Welcome, and thank you for joining The Sleepy Scientist. This space is made for quiet curiosity, a place to drift towards sleep while learning about the hidden patterns and stories behind the world around you. Tonight's video is all about chemistry, the invisible architecture of everything. From the breath in your lungs to the stars that forge the elements inside you, chemistry explains it all. Before we begin, I'd love to know, where are you watching from tonight? Maybe you're curled up somewhere warm or letting your eyes rest after a long day. If you're new here, it would mean a lot if you left a like and subscribe to the channel. It helps this little corner of calm science reach more sleepy minds. And to those already subscribed, thank you. You make these late-night explorations possible. If you haven't already, you can also tap the notification bell so you don't miss the next journey. I hope this video isn't too interesting that it keeps you awake, but if it does, at least you'll drift off a little wiser. Now, before you close your eyes and let the world slow down, here's a question to keep floating gently in your thoughts. What if every spark, scent, colour and heartbeat you've ever known could be traced back to the quiet dance of just a few tiny particles? Chemistry is the story of transformation. It is the bridge between physics, the rules of the universe, and biology, the life that follows those rules. It tells us why things burn, shine, rust, melt, heal, and explode. It reveals how atoms assemble themselves into water, DNA, and the very air that carries your breath. For as long as humans have looked at fire, mixed herbs, or polished metal, we've practiced chemistry, even before we had a name for it. Alchemists once sought to turn lead into gold, but what they really uncovered was something even more valuable, the first glimpses of how matter changes. In this video, we'll wander through the chemistry of everything, from atoms and bonds to stars and life. You'll hear 300 carefully chosen facts, explained slowly and clearly, each one another piece in the mosaic of matter. By the end, you might see your world, your body, your home, your planet, in a completely new light. So settle in, breathe deeply, and let's begin our long, gentle journey into the quiet world of chemistry, the science that turns the ordinary into the extraordinary. Imagine matter not as a solid block, but as a surprisingly spacious construction. Almost everything is empty. An atom's mass is squeezed into a tiny nucleus, while electrons inhabit a diffuse cloud around it. If the nucleus were the size of a small seed placed at the centre of a sports stadium, the electrons would be whirling somewhere near the outer stands, and the rest would be open air. That is how airy the foundations of the solid world truly are. The electrons do not circle like planets on tidy rails. Instead, they occupy orbitals, regions of probability where an electron is likely to be found. It is a haze with rules, a map of likelihoods rather than a set of tracks. This picture explains why atoms can form bonds, why light is absorbed and emitted in neat colours, and why the seemingly solid table under a resting hand is mostly organised space. At the heart of that space sit protons, and protons decide identity. Count them and you name the element. 1 proton means hydrogen, 2 means helium, 6 means carbon, 8 means oxygen. Change the proton count and the element changes with it, the way a single digit in a phone number transforms the person reached on the other end. This is the atomic number, the simplest label in chemistry and the most decisive. The number of protons is like a passport that cannot be forged. Add 1 and the entire passport changes nations. Protons do not sit alone. Neutrons share the nucleus, adding mass and helping to glue the structure together. They carry no electric charge, yet their presence is crucial for stability. Vary the neutron count while keeping the protons the same, and you create isotopes, versions of the same element with slightly different weights. Carbon with 6 protons and 6 neutrons. Carbon-12 is stable and common. Carbon with 6 protons and 8 neutrons. Carbon-14 is heavier and slowly decays, a quiet clock that has helped date ancient wood and bone. Even water can carry a subtle twist. Replace normal hydrogen with its heavier sibling deuterium and the water still looks like water, yet it flows and freezes a little differently. Chemistry stays familiar, but the rhythm changes. Electrons, the lightweights of the atom, behave with strict restraint. They may only occupy certain energies, never anything in between. Imagine a staircase in the dark, and the feet can land only on steps, not hover mid-air. Give an electron just the right amount of energy, and it can hop to a higher step. Let it fall back, and it releases that exact amount, often as a photon of light. This quantized dance is the reason hot metals glow, fireworks paint the night with distinct hues, and stars carry barcodes in their spectra that reveal what they are made of. The pattern of allowed energies is unique to each element, turning every atom into a tiny instrument with its own set of notes. When estimating how heavy an atom is, all eyes return to the nucleus. Protons and neutrons contribute almost all the mass. Electrons are so light that, for most purposes, their weight is a rounding error. Add up the protons and neutrons and you have a good approximation of the atomic mass. This simple arithmetic turns out to be powerful. It predicts how much a sample weighs, how much energy a reaction might release or absorb, and how much of a product can be made from given ingredients in a beaker. It is the quiet bookkeeping that keeps chemistry honest. Yet the personality of an element, the way it bonds, reacts, and forms the stuff of life, belongs mostly to the electrons farthest from the nucleus, the valence electrons. These outermost electrons are the ones that meet other atoms at the border and decide whether to share, trade, or keep to themselves. Sodium has one valence electron and is eager to pass it on. Chlorine craves an extra electron and gladly accepts. When sodium hands over its lone valence electron to chlorine, the result is a stable, neutral partnership recognized as common table salt. Noble gases with comfortably filled valence shells are generally aloof, rarely bothered to react at all. Shift just one electron into or out of that valence shell, and the change in behavior can be dramatic. That is why rows and columns in the periodic table carry patterns. Elements in the same column share similar valence arrangements and often act like relatives at a reunion, different in details, similar in temperament. So the atom story is threefold: a dense, tiny center that sets identity and weight, a set of neutrons tuning stability, and a faint rule-bound cloud of electrons that writes the script of chemical behavior. From these simple parts, protons, neutrons, and electrons, arise colors in a flame, rust on iron, the fizz of a drink, and the breath moving in and out of a chest. Chemistry begins here, in the mostly empty space that somehow builds a world. Picture the atom as a softly lit sphere with nothing solid to touch. Most of its size is the electron cloud, and that cloud is a map of likelihood, not a shell you could peel away. An orbital says, the electron is likely to be found here, the way a weather map says rain is likely in a certain region. Sometimes the electron is closer in, sometimes farther out, sometimes in lobes that look like balloons or clover leaves, but it is always about probability. This is why the word cloud fits so well. It is real, measurable and patterned, yet never a rigid surface. Holding court at the centre is the nucleus, a dense knot of protons and neutrons packed together by the strong nuclear force. Protons would normally repel one another, positive charges push apart, but at extremely short distances the strong force overwhelms that repulsion and binds them tightly, with neutrons boosting the stability of the arrangement. Think of it as the most powerful glue nature uses, working only when the particles are almost touching. Without this intimate short-range force, nuclei would fly apart, and the periodic table would collapse into a drift of lonely protons. The labels we give elements carry stories from languages long travelled. Atomic symbols are often short and familiar, C for carbon, O for oxygen, but some wear their history on their sleeve. Na comes from natrium, K from kalium, and Fe from ferrum, the Latin word for iron. These symbols are a compact chemistry alphabet that lets equations stay crisp and universal across languages. Whether you're reading a textbook in English, Spanish, or Japanese, Phi still points to the same tough, silvery metal that built railways and bridges. To compare the masses of these atoms cleanly, chemists agreed on a tidy yardstick, the unified atomic mass unit. It is defined so that one atom of carbon-12, carbon with 6 protons and 6 neutrons, weighs exactly 12 units. Everything else is measured relative to that. Hydrogen comes in at just about 1 unit. Oxygen settles near 16. You do not need to memorize the decimals to get the point. This definition is like setting the scales 0 and the size of each tick mark so everybody's measurements line up. When atoms change their charge, they do it the easy way, by moving electrons, not by rearranging the nucleus. Ionization is the process of turning a neutral atom into an ion by losing or gaining electrons. Strip an electron away and the atom becomes positively charged. Tuck an extra electron in and it becomes negatively charged. The proton count inside the nucleus does not budge during ordinary chemistry, because changing that would mean nuclear reactions, not everyday bonds and solutions. In the gentle realm of beakers and batteries, it is the nimble electrons that shuffle, not the anchored protons. From that simple shuffle come 2 families with opposite personalities. Lose electrons and you get cations, positively charged species. Gain electrons and you get anions, negatively charged species. If you like mnemonics, remember that cations are positive. Sodium tends to become a cation with a single positive charge, written as sodium plus. Chlorine prefers to become an anion with a single negative charge, written as Cl minus. When they meet, their opposite charges pull them together into sodium chloride, better known as table salt. In water, those ions separate and move freely, which is why salty solutions conduct electricity so well. The world of charge is courteous and predictable. Opposites attract, like charges repel, and the dance of cations and anions quietly powers nerves, batteries, and the chemistry of life. Isotopes are like siblings in the same family. They share the same number of protons, so their chemical personalities match, but they carry different numbers of neutrons, so their masses differ. That small change in weight can lead to gentle shifts in behaviour. Swap ordinary hydrogen, protium, for its heavier sibling deuterium, and you get heavy water. It still looks like water and splashes like water, but it freezes, boils and flows just a little differently because each molecule is, quite literally, heavier on its feet. Chemically familiar, physically distinct. That is the quiet charm of isotopes. One isotope, carbon-14, carries a built-in clock. It forms high in the atmosphere and ends up in living things, joining the carbon already in their tissues. While an organism is alive, the ratio of carbon-14 to carbon-12 stays steady. After it dies, the carbon-14 slowly decays, tick by tick. By measuring how much remains, scientists can estimate the time since death. Not to the exact day, but well enough to place artifacts, wood or bone, within tens of thousands of years. It is a dating method written by the atom itself, a gentle glow that fades on a schedule. Some isotopes are chosen for their helpful signals inside the body. In hospitals, technetium-99m, the M stands for metastable, is a favourite because it emits photons that cameras can detect while delivering a relatively low radiation dose. Attach it to a compound that targets a particular organ, and physicians can watch blood flow, bone turnover, or heart function in real time. The isotope is the tracer. Biology provides the map. The moment it has done its job, it decays to a more stable form, and the image becomes a record of the body's chemistry at work. Stable isotopes tell stories at a planetary scale. Take oxygen-18 and oxygen-16, water molecules containing the heavier oxygen. 18 evaporate and condense just a bit differently than those with oxygen-16. Over seasons and millennia, that tiny preference is captured in snow layers that turn into ice and in the shells of ancient marine organisms. By measuring the oxygen-18 to oxygen-16 ratio in an ice core or a fossil shell, scientists can reconstruct past temperatures and rainfall patterns. It is like reading Earth's diary, where every page is written in oxygen's subtle handwriting. Behind these signals is a simple physical tendency called isotopic fractionation. Lighter isotopes move, vibrate, and diffuse a little faster. They are slightly more likely to evaporate first, to zip through membranes, or to take part in reactions that favour speed. Heavier isotopes lag just a hair behind. In a single glass of water, the difference is invisible. Across oceans, ice sheets, and ages, the pattern becomes clear. Nature separates the nearly indistinguishable, and the separation turns into a clue. At the heavy end of the chart, uranium offers a different lesson. Uranium-235 is fissile, meaning that when it absorbs a neutron, it can split into smaller nuclei, releasing energy and more neutrons that can keep the process going, a chain reaction. Uranium-238 is far more abundant in natural uranium, but it is less reactive in that way. It does not readily sustain a chain reaction. That contrast, scarce but eager versus common but reluctant, underpins how nuclear reactors are fueled and how enrichment works. One isotope is the match, the other is the pile of wood. Together they remind us that changing only the neutron count can reshape the possibilities of an element, from dating ancient charcoal to lighting modern cities. Radioactive decay has a calm predictability to it. It follows first-order kinetics, meaning the rate at which a sample decays is directly proportional to how much of it is present. The key idea is the half-life, the time it takes for half the atoms in a sample to transform into something else. After one half-life, half remains. After two half-lives, 1/4. After three, 1/8. The clock does not speed up or slow down with temperature or pressure the way ordinary chemical reactions do. Each nucleus keeps its own quiet schedule, and large crowds of them add up to a smooth statistical fade. Not all decays look the same. In alpha decay, a nucleus emits a compact bundle of 2 protons and 2 neutrons, essentially a helium-4 nucleus, which carries a positive charge and can be stopped by a sheet of paper or even the outer layer of skin. Beta decay changes identity inside the nucleus. A neutron can turn into a proton with the emission of an electron and an antineutrino, beta minus, or a proton can become a neutron with the emission of a positron and a neutrino, beta plus. Gamma decay emits no particles at all, just a photon of high-energy light as the nucleus relaxes from an excited state to a lower one. Think of alpha as a little fragment leaving, beta as a swap of identity inside the nucleus, and gamma as the release of leftover energy. That positron mentioned in beta plus is not just a theoretical guest. It is the star of PET scans, short for positron emission tomography. Doctors attach a positron-emitting isotope to a molecule that cells naturally take up, often something akin to glucose. When the isotope decays, the emitted positron quickly meets an electron, and the pair annihilates, producing 2 photons that fly off in exactly opposite directions. Detectors catch these paired flashes, and computers reconstruct a map of metabolic activity. Bright where cells are ravenous for fuel, dim where they are quieter. In this way, PET turns atomic whispers into images that guide diagnoses and treatments. Sometimes radioactive atoms drift where we live. Radon is a noble gas that seeps from soil and rock as heavier elements decay underground. Being a gas, it can slip into basements and accumulate in still air. Outside, it disperses. Indoors, it can build up, and its decay products can lodge in lungs. Because radon is colourless and odourless, it is usually found only by testing, and ventilation is the simple, effective remedy. It is a reminder that radioactivity is a natural part of Earth's chemistry, one that calls for informed caution rather than panic. On the timescale of Earth itself, radioactive decay writes the planet's calendar. Uranium-238, the most abundant uranium isotope, decays through a long chain of steps until it becomes lead-206, which is stable. Minerals trap uranium when they form, and as the uranium decays, lead accumulates in a predictable ratio governed by the uranium's half-life. Measure the amounts of the parent and the daughter, and you can calculate a formation age for the mineral. This uranium-lead clock has dated some of the oldest rocks on the planet, and even helped set lower bounds on the age of Earth. Isotopic labeling is a gentler trick that chemists use to follow atoms through complicated reactions. Replace a common atom with a harmless isotope, oxygen-18 instead of oxygen-16, deuterium instead of protium, carbon-13 instead of carbon-12, and you can trace where that specific atom goes without changing the overall chemistry very much. In a reaction with many moving parts, the labelled atom is a tiny flag. Spectrometers and other instruments can see the flag even when human eyes cannot, revealing mechanisms step by step, which bond breaks first, which intermediate forms where the oxygen in a product originally came from. It is cartography for molecules, mapping their journeys with just a small nudge to their mass. Electrons arrange themselves in atoms by climbing a ladder of energy, choosing the lowest available rungs first. This general pattern is called the Aufbau principle, building up. Imagine filling seats in a theatre from the front row to the back. The best seats go first, and only when a row is full do people move to the next. In atoms, the rows are orbitals, each with a set capacity and energy. The order is not simply 1, then 2, then 3 by shell number. Because of subtle interactions between the nucleus and the shapes of orbitals, the force orbital fills before the 3D, and similar quirks appear throughout the table. Still, the guiding idea stays simple. Electrons prefer lower energy, and they only climb higher when the comfortable place is taken. There's also a strict rule about sharing those seats. The Pauli exclusion principle says that no two electrons in the same atom can have the exact same set of quantum addresses. In practical terms, this means that an individual orbital can hold 2 electrons at most, and if it holds 2, their spins must oppose each other. One points up, the other down, balancing like tiny bar magnets arranged north to south. This paired arrangement reduces repulsion and keeps the bookkeeping neat. Without the Pauli rule, electrons would have no reason to spread out, and the periodic table, with all its orderly patterns, would unravel. When orbitals of the same energy are available, electrons act a bit like polite guests at a party. They spread out before they start to pair up. This is Hund's rule. If you have, say, 3p orbitals at the same energy, an electron will sit alone in each orbital with parallel spin before any orbital receives a second, opposite spin electron. The effect minimizes electron-electron repulsion and stabilizes the atom. It also explains why certain electron configurations are particularly steady. Half-filled or completely filled, sets of orbitals offer a kind of symmetry and balance that nature quietly prefers. To keep track of capacity, it helps to know the simple head counts. The S subshell has 1 orbital and can hold 2 electrons. The p subshell has 3 orbitals and can hold 6 electrons. The d subshell has 5 orbitals and can hold 10 electrons. The f subshell has 7 orbitals and can hold 14 electrons. Those numbers, 2, 6, 10, and 14, come straight from the number of orbitals multiplied by 2 spins. This tally is more than trivia. It sets the rhythm of the periodic table. As you add electrons across a period, you fill p orbitals one by one, drop to a new block, and you may begin to fill d or f orbitals with their larger capacities and more intricate shapes. While the whole electron arrangement matters, the personality of an element shows up most clearly in its outermost electrons, the valence electrons. These are the electrons that meet other atoms, form bonds, and decide whether a substance is inert, reactive, acidic, basic, metallic, or non-metallic. Elements in the same column of the periodic table tend to have the same number of valence electrons, which is why sodium, potassium, and cesium behave like cousins with similar habits. Change the valence count by even 1, and the chemistry can swing from explodes in water to barely reacts at all. Valence electrons are the negotiators at the border, arranging trades, sharing pairs, or standing aside. Transition metals are a special showcase for how electron configuration shapes behavior. In these elements, the d subshells are being filled, and those d electrons sit close in energy to the s electrons of the outer shell. Because their energies are similar, transition metals can lose different numbers of electrons under different conditions, leading to varied oxidation states. Iron can be iron 2 or iron 3. Copper can be copper 1 or copper 2. This flexibility is one reason transition metals make excellent catalysts. They can switch electron counts and coordinate with different partners without tearing themselves apart. The partially filled d orbitals also allow interesting geometries and colourful complexes, as incoming ligands interact with the d electrons and split their energies, producing vivid shades in solution. Put these ideas together and a pattern emerges. Electrons fill the lowest energy orbitals first, never duplicating a full set of quantum details. They spread out across equal energy seats before pairing. The capacities of s, p, d, and f subshells set the structure of the periodic table. The outermost electrons dictate reactivity, and the d-electron playground of the transition metals opens a world of flexible oxidation states and catalysis. From these compact rules flows the grand variety of chemical behavior, from the passivity of noble gases to the lively colors of metal complexes and the reliable bonds that build life's molecules. Noble gases sit on the far right of the periodic table like contented neighbours who already have everything they need. Their valence shells are full, with no incentive to trade or share electrons, so they mostly ignore the chemical bustle around them. Helium, neon, argon. They are the wallflowers of chemistry, and their calmness is a direct consequence of electronic completeness. A filled outer shell is a finished puzzle, satisfying, symmetrical, and not looking for extra pieces. Every good rule in chemistry has a few elegant wrinkles, and chromium and copper are classic examples. Their ground state electron configurations borrow a little stability by achieving half-filled or fully filled d subshells. Chromium prefers to be written as argon, 4s1, 3d5, rather than argon, 4s2, 3d4, because a half-filled set of 5d orbitals with 1 electron each is especially stable. Copper leans toward argon, 4s1, 3d10, favouring a completely filled d subshell. These choices reflect tiny energy trade-offs that pay dividends in stability, reminding us that electrons are accountants of energy first and rule followers second. When atoms form ions, the departing electrons usually come from the highest principal energy level, not necessarily from the last subshell we wrote when filling. That is why many transition metals lose their 4s electrons before touching their 3d electrons. The force electrons, though filled earlier, sit at a slightly higher principal level and are more easily removed when the atom becomes a cation. It is a subtle ordering. Fill and remove are not mirror images, and chemistry cares about the energy right now, not the historical path the electrons took to get there. As you move across a period from left to right, the effective nuclear charge felt by the valence electrons increases. The nucleus gains protons, but the inner shielding does not increase enough to cancel that extra pull, so the outer electrons are drawn a little closer. Radii shrink, ionization energies rise, and electronegativities climb. The atom tightens its belt. That steady strengthening of attraction helps explain why fluorine is so keen to attract electrons, while sodium, just a few steps away, is happy to let one go. Shielding is the counterbalance to that pull, the way inner electrons blunt the full charge of the nucleus from the perspective of the outer ones. Electrons in lower shells spend more time close to the nucleus, and their negative charge repels outer electrons, reducing how strongly those outer electrons are attracted to the nucleus. Electrons feel the positive nuclear charge. More inner electrons generally mean more shielding, which is one reason atoms grow larger as you go down a group. The nucleus gets stronger, but the layers of electron insulation thicken too, letting the outer shell sit farther out. Underneath all these rules sits a mathematical heartbeat. Atomic orbitals are not little tracks, but solutions to the Schrödinger equation, functions that describe the probability of finding an electron in space. The familiar shapes, the spherical S, the dumbbell-shaped P, the more intricate D and F, are pictures of where the electron is likely to be found, not where it must be. Nodes, lobes and phases emerge naturally from the mathematics, and those features ripple outward into real-world behavior. Bond angles, colors of metal complexes, even the hardness of minerals. The poetry of electron configuration is written in equations, but it is read in the colors of fireworks, the stability of noble gases, and the quiet way atoms decide who they will bond with and who they will politely ignore. Slide your finger across a period of the periodic table from left to right, and atoms quietly pull themselves inward. The effective nuclear charge rises as protons are added to the nucleus, but shielding from inner electrons does not increase enough to cancel that pull. Valence electrons are drawn closer, so atomic radius generally shrinks across a period. Now trace downward in a column, and the trend flips. New shells are added. Shielding increases, and the outer electrons sit farther from the nucleus. Atomic radius grows as you move down a group, giving cesium a much roomier electron cloud than lithium. That tightening across a row and loosening down a column explains a twin trend in ionization energy, the energy needed to remove an electron. When electrons are held closer and more tightly, prying one loose takes more effort. Ionization energy generally increases across a period and decreases down a group. Helium hangs on with determination. Cesium lets go with a shrug. There are small bumps and dips caused by subshell structures. Pulling the first electron from a full or half-full subshell can cost a bit more, but the broad sweep is clear. Compact atoms cling, spacious atoms share. A related measure, electron affinity, tracks the energy change when a neutral atom gains an electron. As you move across a period, atoms are usually more eager to accept an extra electron to complete or approach a filled valence shell, so electron affinities tend to become more negative, meaning more energy is released. The pattern is not perfectly smooth, because orbital shapes and electron-electron repulsions introduce local quirks. For example, filling a p orbital that is already half full can sometimes be less favourable than expected. Still, the idea holds. Atoms that are already pulling their electrons close often welcome one more with a satisfying snap. electronegativity ties these ideas together in the context of a bond. It is a comparative scale of how strongly an atom attracts shared electrons when it is covalently bonded. Across a period, electronegativity increases as atoms become smaller and nuclear pull grows. Down a group, it decreases as distance and shielding weaken the grip. At the top of this scale sits fluorine, the champion of electron tug-of-war. Give fluorine an opportunity to share, and it pulls the shared pair toward itself, polarizing the bond. This simple gradient from low electronegativity metals on the left to high electronegativity nonmetals on the right helps predict which bonds are mostly ionic, which are polar covalent, and which are nearly nonpolar. All of this plays into metallic character, the broad set of behaviors associated with metals, a willingness to lose electrons, formation of positive ions, and the capacity to conduct heat and electricity. Metallic character increases as you go down a group and decreases as you move across a period. Sodium, magnesium, aluminum. Each step to the right softens the metal's readiness to donate electrons, and by the time you reach silicon and phosphorus, the character has shifted toward metalloids and then nonmetals. Head down a column though, and the atoms grow larger, and their outer electrons are held more loosely, restoring that easy electron donation that metals are known for. You may notice that noble gases often do not appear on electronegativity charts. There is a simple reason. They rarely form bonds at all, so assigning them a value on a bonding-based scale can be misleading. Their filled valence shells make them largely uninterested in sharing electrons, which means there is not much real-world data to anchor a number. In exceptional conditions, some noble gas compounds do form, especially with xenon, but for everyday chemistry the noble gases sit out the tug-of-war, and the scale focuses on the players who actually take the field. Put the map together and the periodic table becomes less a list and more a landscape. Radii shrinking across, swelling down. Ionization energy is rising across, falling down. Electron affinities growing more exothermic across with gentle exceptions. Electronegativities peaking at fluorine and fading toward the corners. Metallic character blooming down the left side and withering toward the upper right. And noble gases watching calmly from the sidelines. With these contours in mind, trends stop being facts to memorize and start becoming features you can navigate, predicting how unfamiliar elements will behave long before you meet them in the lab. Group 1, the alkaline metals, are the sprinters of reactivity. Give them water and they leap into action, each atom eager to lose its single valence electron and become a +1 cation. The result is a hydroxide solution, and a puff of hydrogen gas that can ignite if the reaction runs hot enough. In simple stoichiometry, 2 sodium solid plus 2 water liquid yields 2 sodium hydroxide aqueous plus hydrogen gas. Lithium tends to fizz politely. Sodium zips along. Potassium, rubidium, and cesium can turn downright theatrical. The underlying reason is straightforward. As you move down the group, the outer electron sits farther from the nucleus and is more easily removed, so the reaction gets faster and more exothermic. Next door in group 2, the alkaline earth metals prefer a measured pace. They commonly form +2 cations by shedding 2 valence electrons, landing in the comfortable stability of a noble gas-like configuration. They are less reactive than their group 1 neighbours, because losing 2 electrons takes more energy than losing 1. Magnesium and calcium react with water, but usually more slowly and often requiring heat or finely divided surfaces to get going. Their hydroxides are less soluble across the group, which is why magnesium hydroxide shows up as a milky antacid, and calcium compounds build seashells, limestone, and the sturdy backbone of concrete. Group 17, the halogens, are chemistry's avid collectors. With 7 valence electrons, they are one short of a filled shell and very keen to complete it, which makes them highly reactive nonmetals. Pair a halogen with a metal, and you get a salt, a neat ionic lattice born from electron transfer. Sodium plus chlorine forms sodium chloride, calcium plus bromine forms calcium bromide. Down the group, reactivity softens a bit as atoms grow and the added electron sits farther out, but the appetite for that final electron remains. In element form they span phases and colours: pale green chlorine gas, red-brown bromine liquid, deep purple iodine solid. Yet they all share the same craving for completion. On the far right, the noble gases often watch the action from a polite distance, but even the quiet ones have their adventurous days. Under extreme conditions, powerful oxidizers, high pressures, or excited states, heavier noble gases can form compounds. Xenon is the standout, bonding with fluorine to make xenon difluoride, xenon tetrafluoride, and xenon hexafluoride. These are stable enough to bottle and study, proof that unreactive in chemistry usually means unreactive under ordinary conditions. The heavier the noble gas, the more its outer electrons are polarizable, and the more likely unusual bonds can form when pushed. Transition metals are the nimble multitaskers of the table. With d subshells close in energy to their outer electrons, they can adopt multiple oxidation states and coordinate to a changing cast of ligands. That flexibility, switching electron counts, binding and releasing partners, and stabilizing different intermediate states, is exactly what a good catalyst needs. Iron can cycle between iron 2 and iron 3. Manganese marches through a whole parade from manganese 2 up to manganese 7. Palladium shuffles between oxidation states as it stitches carbon chains together in coupling reactions. Because catalysts are not consumed, a pinch of the right metal complex can steer a reaction down a smoother path, lowering the activation energy and boosting yield without rewriting the final recipe. Tucked beneath the main body of the table, the lanthanides form a close-knit family of F-block elements with remarkably similar chemistry. Their valence behaviour is dominated by a +3 oxidation state, and their F electrons are largely shielded, so they do not vary wildly from one neighbour to the next. That sameness made them notoriously tricky to separate historically, but it also gives them a suite of shared talents: strong magnetic moments, sharp spectral lines, and a knack for phosphorescence. Europium brings the red to television and phone screens, terbium lights up green, neodymium lends magnets their muscle in compact motors and headphones. Subtle differences in ionic radius, the lanthanide contraction as the series progresses, fine-tune their coordination chemistry, but the headline remains: similar size, similar charge, similar behaviour, especially as +3 cations. Seen together, these groups sketch the table's personality: alkali metals eager to give 1 electron, alkaline earths calmly handing over 2, halogens hungry to take 1 back, noble gases mostly content but capable of surprises, transition metals acting as adaptable catalysts, and lanthanides humming along in +3, lighting up technology and sharpening images with their spectral signatures. The periodic trends are not just arrows on a chart. They are habits written by electrons predicting who reacts with whom, how fast and to what end. Ionic bonding is the quiet pull between opposites. A metal atom that easily lets go of an electron becomes a positively charged cation. A non-metal that eagerly accepts that electron becomes a negatively charged anion. Place them near each other and electrostatic attraction does the rest. You can picture it in steps. Sodium solid gives up 1 electron to become sodium +1. Chlorine gas accepts 1 electron to become chloride -1. Then sodium +1 and chloride -1 assemble into a neutral crystal of sodium chloride. The bond is not a shared pair like a covalent handshake. It is the persistent tug of unlike charges holding a lattice together. The firmness of that lattice is captured by lattice energy. the energy released when gaseous ions pack into a solid. Smaller ions can get closer, and higher charges tug harder, so both of those raise lattice energy. Magnesium oxide with magnesium +2 and oxide -2 binds far more tightly than sodium chloride with +1 and -1. That is why magnesium oxide has a much higher melting point. Stronger attractions mean more heat is needed to pry the ions apart. In short, the more compact and more highly charged the ions, the sturdier the ionic solid. Ionic solids are full of charges, yet a cool, intact crystal will not carry electricity through itself. The ions are locked in place, unable to move as charge carriers. Melt the crystal, however, and the ions are free to drift. Dissolve it in water, and the ions separate and swim. In either case, mobile charge particles are available, and the liquid conducts. This simple switch, fixed in a solid, free in a melt or solution, is why table salt does not conduct on your shelf, but salty water lights up a conductivity probe. That rigid arrangement also explains why many ionic compounds are brittle. Press on a crystal, and, if layers slip just enough, rows of like charges can be forced to face each other. Positive against positive, negative against negative. Repulsion spikes and the crystal cleaves along a plane. Instead of bending like a metal, the ionic lattice snaps. The neat flat faces of salt crystals are the geometric fingerprints of that ordered yet fragile arrangement. Water can unravel these lattices because it hydrates ions, surrounding them with oriented molecules that stabilize the charges. Ion size and charge density tip the balance between lattice energy, which holds ions together, and hydration energy, which pulls them apart. Small, highly charged ions have intense electric fields and attract snug, structured shells of water. Large, diffuse ions interact more gently. When hydration energy outweighs lattice energy, the salt dissolves readily. That is why sodium nitrate dissolves easily, while some sparingly soluble salts, like barium sulfate, resist. Their lattices are simply too strong to be compensated by hydration. Among the ions that roam in water, oxyanions are especially common. These are polyatomic anions with oxygen, atom bonded to a central nonmetal, and their structures often spread negative charge through resonance, which stabilizes them. Nitrate, written as NO3-1, and sulfate, written as SO4-2, are classic examples. Their oxygen frameworks make them versatile partners in chemistry, from plant nutrition to atmospheric processes. Because the negative charge is shared across several atoms, oxyanions are generally quite stable in solution and form a wide variety of salts, some highly soluble, some stubbornly not, depending on how their charge and size match up with the cations they meet. A covalent bond is a shared story between atoms. Instead of handing electrons over, they hold a pair between them. The strength of that partnership depends on bond order, how many shared pairs there are. A single bond shares one pair, a double bond shares two, a triple bond shares three. As bond order increases, the bond usually grows stronger and shorter. Carbon-carbon single bonds are longer and easier to stretch than carbon-carbon triple bonds, which are compact and tough, like a tightly drawn rope compared with a loose cord. This simple ladder, single, double, triple, is one of the most reliable guides to how rigid or flexible a molecule will be. Under the hood, those shared pairs live in overlapping orbitals. A sigma bond is the head-on overlap of orbitals along the line between the two nuclei, the simplest, most direct connection. A pi bond is different. It forms from the side-by-side overlap of p orbitals above and below the bonding axis. Every single bond is a sigma bond. A double bond contains one sigma plus one pi bond, and a triple bond contains one sigma plus two pi bonds. Think of sigma as the backbone and pi as the reinforcing beams that add strength and shape. Because pi bonds are formed by that side-on locking of electron clouds, they resist twisting. A single bond, just sigma, can rotate fairly freely at room temperature. Groups can spin around that axis like beads on a string. Add a pi bond, and rotation becomes restricted. Twist too far and you would have to break the pi overlap. That is why alkenes can have distinct E and Z, or cis and trans arrangements. The double bond freezes parts of the molecule into place. This rigidity shapes everything from the scent of molecules to the colours of dyes and the behaviour of biological membranes. Not all shared pairs are shared equally. Bond polarity arises when one atom pulls on the shared electrons more strongly than the other. The measure of this tendency is electronegativity. A large difference means a more polar bond, with electron density shifted toward the more electronegative partner. In a hydrogen-fluorine bond, the electrons huddle closer to fluorine, giving it a partial negative charge and leaving hydrogen a partial positive. Stack many polar bonds in a molecule, and their directions matter. Sometimes the polarities cancel, sometimes they reinforce to create a strongly polar molecule that mixes well with water and interacts keenly with ions. Resonance adds a layer of elegance to this picture. Some molecules cannot be well described by a single drawing of bonds and lone pairs. Instead, electrons are delocalized across multiple positions, and several contributing structures, resonance forms, blend into a more accurate hybrid. Nitrate, written as NO3-1, is a classic example. The negative charge and the pi bonding are spread evenly over the three oxygens, making all nitrogen-oxygen bonds equivalent in length and strength. Benzene's ring is another. The pi electrons circulate over the entire hexagon, producing equalized carbon-carbon bonds and an extra measure of stability known as aromaticity. Resonance is not electrons jumping back and forth. It is a way of acknowledging that electrons are shared over a broader canvas. For many main group molecules, the octet rule offers a tidy goal. Atoms often arrange themselves so that each has 8 electrons in its valence shell. It is a helpful guide, but it is not a law. Some molecules have expanded octets because their central atoms can access d orbitals and accommodate more than 8 electrons. Phosphorus pentachloride and sulfur hexafluoride are straightforward examples. Phosphorus and sulfur sit in environments where 5 or 6 bonding pairs can be held stably. On the other side, electron-deficient molecules make do with less than an octet. Boron trifluoride famously stops at 6 valence electrons around boron, yet it is a stable compound under ordinary conditions. In between are radicals with unpaired electrons and odd electron counts, and hypervalent ions that stretch the bookkeeping in polar environments. The octet rule is best treated as a compass, not a cage. It points in the right direction most of the time, while chemistry keeps a few scenic detours for special cases. Put together, these ideas make covalent bonding feel both intuitive and rich. Shared pairs that tighten with higher bond order, sigma backbones and pi reinforcements, double bonds that lock shapes and create geometric isomers, electronegativity pulling charge to sculpt polarity, resonance spreading electrons for stability, and octet guidelines that bend gracefully when the energy landscape allows. From the fragrance of an orange to the strength of Kevlar and the base pairs of DNA, this is how atoms cooperate to build the textures, colours, and structures of the world. Molecules choose their shapes by giving their electrons some personal space. That is the simple wisdom of VSEPR, valence shell electron pair repulsion. Around a central atom, regions of electron density, bonding pairs and lone pairs, arrange themselves as far apart as possible to minimize repulsion. Count the regions, spread them out symmetrically, and you have the basic geometry. Attach the atoms to those regions and the shape appears. With 2 regions, you get a straight line. With 3, a flat triangle. With 4, a 3-dimensional tetrahedron. It is a tidy rule of "back off a bit please," played by electrons. Not all electron pairs push equally hard. Lone pairs, electron clouds that belong to the central atom alone, repel more strongly than bonding pairs that are shared between atoms. That extra shove squeezes nearby bond angles slightly. Water is a classic example. Its electron geometry is tetrahedral, but because 2 of those positions are lone pairs, the HOH angle compresses below the comfortable tetrahedral angle, and the molecule becomes bent. Ammonia shows the same idea in 3 dimensions. 3 NH bonds and 1 lone pair arranged tetrahedrally in electron terms, but the shape you see is trigonal pyramidal with slightly pinched angles, because that lone pair elbows the bonds a little closer together. From that logic, a short gallery of common shapes follows. 2 regions make linear molecules like carbon dioxide, where electron clouds sit opposite each other. 3 regions make trigonal planar molecules like boron trifluoride, flat and evenly spaced. 4 regions give tetrahedral molecules like methane, a shape that spreads bonds to the corners of a pyramid with a hidden center. 5 regions create trigonal bipyramidal structures like phosphorus pentachloride, with 3 bonds around the equator and 2 at the poles. 6 regions produce octahedral molecules like sulfur hexafluoride, where 6 identical positions radiate from the center like spokes on a perfect wheel. Each geometry is just the most peaceful way to sit when everyone wants elbow room. Whether a whole molecule is polar depends on 2 things at once: the polarity of the individual bonds and the way those bonds are arranged in space. Carbon-oxygen bonds are polar, for example, but in carbon dioxide they point in opposite directions and cancel each other, leaving a non-polar molecule. In water, the 2 polar OH bonds are not arranged in a line. They meet at an angle, and their polarities reinforce to give the molecule a permanent dipole. That is why water loves to dissolve ions and other polar substances. Geometry does not simply decorate a molecule, it decides how charges add up or cancel out. Hybridization offers another lens to make sense of these shapes and the equal bonds they contain. In methane, the carbon mixes one s orbital with 3 p orbitals to form 4 equivalent sp3 hybrids, each pointing toward a corner of a tetrahedron. That is why all 4 CH bonds are identical and evenly spaced. In ethene, each carbon uses sp2 hybrids to form a flat trigonal arrangement with 1 unhybridized p orbital left over. Those 2 p orbitals overlap side by side to make a pi bond, locking the double bond and restricting rotation. In ethene, the carbon atoms use sp hybrids to line up in a straight line, with 2 perpendicular p orbitals on each carbon forming 2 pi bonds for a triple connection. The hybrid story is a convenient way to explain why bonds that look the same really are the same. Delocalization brings a special kind of calm to certain molecules, especially aromatic rings. In benzene, the 6 carbon atoms form a hexagon with alternating single and double bonds in a simple drawing, but the electrons that make those pi bonds are actually spread evenly around the ring. The result is that all carbon-carbon bonds become equal in length and strength, somewhere between a single and a double bond. This shared circulating electron cloud grants unusual stability, aromatic stability, and gives rise to distinct reactivity and characteristic spectroscopic fingerprints. You see the effects in everything from the fragrance molecules of essential oils to the pigments that make dyes vivid. Put together, these ideas turn a flat formula into a 3-dimensional character. Electrons repelling to set the stage, lone pairs nudging the angles, common geometries emerging from simple counts, polarity arising from both bonds and layout, hybrid orbitals explaining identical bond sets, and delocalized pi systems smoothing out bond lengths into symmetrical, unusually stable frameworks. Once you start seeing molecules in shapes rather than strings of letters, their behaviors, boiling points, solubilities, colors, and reactions begin to feel inevitable. Even the calmest molecules tug on each other. The faintest pull is London dispersion. Tiny, momentary dipoles that pop in and out of existence as electrons slosh within a molecule. One instant a molecule has a little more electron density on one side, and its neighbour responds in kind. The next instant the ripple has moved. Every substance has these forces, from noble gases to long-chain hydrocarbons, and they grow stronger as molecules get larger and more polarizable. That is why iodine, with its generous electron cloud, is a solid at room temperature, while the much smaller fluorine is a gas. More electrons, softer clouds, stronger flickers, higher boiling points. Layered on top of that are dipole-dipole interactions, attractions between molecules that have permanent separation of charge. Point a polar molecule's partially positive end toward another's partially negative end, and they align like tiny compasses. These alignments are not as fleeting as dispersion. They add an extra stickiness that raises boiling points and melting points compared with similarly sized non-polar molecules. Acetone and propane are close in size, yet acetone boils much higher because its carbon-oxygen bond creates a standing dipole that molecules can line up around. There is a special, stronger case of this polar pull called hydrogen bonding. When hydrogen is covalently attached to nitrogen, oxygen, or fluorine, the bond is extremely polar, leaving hydrogen with a pronounced partial positive charge. That hydrogen can then interact strongly with a lone pair on nitrogen, oxygen, or fluorine in a neighbouring molecule. The result is a directional cooperative attraction that is stronger than ordinary dipole-dipole forces, but still weaker than covalent bonds. These links knit molecules together into transient networks. Alcohols cling, amides organize, DNA base pairs zip and unzip with exquisite reliability. Replace a single hydrogen bond donor or acceptor, and the texture of a liquid, its solubility, even its aroma can change noticeably. When intermolecular forces strengthen, bulk properties respond. Liquids become more viscous because molecules have a harder time sliding past one another. They pour slowly like honey or glycerol. Surface tension rises, pulling the surface taut enough for small objects or insects to rest on it. Boiling points climb because it takes more energy to separate molecules into a gas. Each property is simply a different outward sign of the same inward story. Stronger attractions demand more effort to overcome. Water is the poster child for hydrogen bonding effects. Each water molecule can form up to 4 hydrogen bonds, 2 through its hydrogens, 2 through the lone pairs on oxygen, creating a constantly rearranging network. That network is why water's boiling point is unusually high for such a small molecule, why its heat capacity is generous, and why ice floats. The open, tetrahedral arrangement in ice makes it less dense than the liquid. In day-to-day terms, it is why a coastal climate is tempered by the ocean, and why a cup of tea stays warm longer than an equal mass of air would. Sometimes ions join the dance. Ion-dipole forces come into play when a charged ion meets a polar molecule. The classic scene is salt dissolving in water, sodium +1 and chloride -1 separate from the crystal, and become surrounded by oriented water molecules. Oxygen atoms face sodium, hydrogens face chloride. These hydration shells stabilize the ions in solution, paying back the energy cost of pulling the lattice apart. The stronger the ion-dipole attraction and the more favourable the hydration, the more readily an ionic compound dissolves. This is also why salt solutions conduct electricity. The ions, now mobile and well solvated, can carry charge through the liquid. These forces do not exist in isolation. They stack and compete. A large non-polar molecule may rely almost entirely on dispersion and still be a waxy solid if its electron cloud is broad and floppy. A smaller but strongly polar molecule may boil higher than a larger nonpolar one because its dipoles lock together. Add a few well-placed hydrogen bond donors and acceptors, and the liquid turns syrupy. Remove them, and it thins. Switch from water to a less polar solvent, and ion-dipole stabilization weakens, changing solubility. Once you learn to read these invisible tugs, dispersion for everyone, dipoles for the polar, hydrogen bonds for N and H, OH and FH, and ion dipole for charged guests, the everyday world starts making chemical sense. Why perfumes linger, why oils bead on a raincoat, why a pinch of salt melts ice, and why water, humble and abundant, behaves like nothing else. Some solids are held together so completely that the word molecule barely applies. In network covalent materials like diamond and quartz, every atom is bonded directly to its neighbours in a continuous three-dimensional framework. There are no discrete units to drift apart, just an endless lattice of strong covalent bonds. To melt such a structure, you must break a vast number of those bonds all at once, which is why their melting points soar and why diamond is so famously hard. Quartz, built from silicon-oxygen tetrahedra sharing corners throughout the crystal, owes its durability and clarity to the same principle. When the entire solid is one bonded network, heat and force have a lot of work to do. Metals take a different approach to togetherness. In metallic bonding, positively charged metal ions sit in a regular array bathed in a sea of delocalized electrons. These mobile electrons are not tethered to any single atom. They drift through the lattice, which explains two classic metallic traits at once. First, conductivity. Push on electrons at one end with a voltage, and they flow easily through the material, carrying charge and heat. Second, malleability. When you hammer a metal, layers of atoms can slide without shattering the crystal, because the electron sea continues to hold the ions together. Instead of like charges snapping into alignment and repelling, the glue reforms on the fly and the sheet bends rather than breaks. Carbon showcases both extremes in a single element. In diamond, every carbon is sp3 hybridized, locked into a tetrahedral network. In graphite, carbon is sp2 hybridized, forming flat hexagonal sheets with strong sigma bonds in the plane and a cloud of delocalized pi electrons above and below. Those pi electrons can roam along the layers, giving graphite good electrical conductivity in plane. Between layers, only weak dispersion forces hold the sheets together, so they slide easily. The reason graphite makes a good lubricant and why a pencil leaves a trail of carbon sheets that shear off under light pressure. Same element, new geometry, utterly different properties. When it comes to dissolving, the guiding idea is pleasantly simple, like dissolves like. Polar and ionic substances dissolve best in polar solvents, where dipole-dipole and ion-dipole attractions can replace the interactions they had in the solid. Nonpolar solutes prefer nonpolar solvents, where dispersion forces do the heavy lifting without being outcompeted by strong solvent-solvent attractions. Drop sodium chloride into water, and the partial negative oxygen atoms face sodium, while the partial positive hydrogens face chloride, stabilizing both ions. Try to dissolve the same salt in hexane, and the ions remain lonely and undisturbed, with little incentive to separate. Flip the example for grease. Oils ignore water, but mingle happily with hexane or toluene, where their soft electron clouds find compatible company. At the boundary between oil and water, a special class of molecules earns its keep. Surfactants have a split personality, a hydrophobic tail that shuns water and a hydrophilic head that embraces it. When sprinkled into a mixture, These molecules march to the interface and line up, tails in the oil, heads in the water, like tiny bilingual diplomats. This neat arrangement lowers surface tension, making it easier to form droplets and films. At higher concentrations, surfactants assemble into micelles, little spheres with the oily tails tucked inside, which can trap grease and carry it away in the wash. The result is the everyday magic of soaps and detergents. By rewriting the interfacial chemistry, they turn stubborn stains into cooperative guests. Water can also build more elaborate structures when pressured into unusual company. Clathrate hydrates are crystalline cages made of water molecules linked by hydrogen bonds, forming spacious cavities that can trap gas molecules such as methane or carbon dioxide. The gas molecules do not form ordinary chemical bonds to the water. They are physically enclosed, stabilized by the surrounding cage. In the chilly, high-pressure realms under ocean floors and in permafrost, vast deposits of methane hydrate store enormous amounts of gas in solid form. Release the pressure or warm the system and the cages collapse, freeing the gas molecules. This behavior fascinates energy researchers and climate scientists alike, because clathrates blur the line between ordinary ice and a gas reservoir. All of these examples, the unbroken grids of diamond and quartz, the electron sea of metals, the layered conductivity of graphite, the like dissolves like rule of solutions, the choreography of surfactants at interfaces, and the icy cages of clathrates, are variations on a theme: how attractions beyond a single covalent bond shape the feel of matter. Change the way electrons are shared or allowed to roam, and you change hardness, melting point, solubility, slipperiness, and the ability to carry charge. The properties we touch and see are the surface ripples of these quiet, microscopic arrangements. Chemistry keeps its promises by balancing the books. A balanced chemical equation conserves atoms and charge. Whatever kinds and numbers of atoms you start with must be the same kinds and numbers you finish with, and total charge must match on both sides. The coefficients in front of formulas are not decoration. They are the molar ratios that tell you how many moles of each substance react together. If the equation reads 1 nitrogen gas plus 3 hydrogen gas yields 2 ammonia, that 1 to 3 to 2 is a precise recipe at the mole scale. Change the amounts you use, and those ratios tell you what should happen if everything goes perfectly. To scale a recipe up or down, you need a translator between the lab scale of grams and the counting scale of moles. That translator is molar mass. Moles equal mass divided by molar mass. If a sample of carbon dioxide weighs 44 grams and its molar mass is 44 grams per mole, then you have 1 mole. If you have 22 grams, you have 1/2 mole. This simple division unlocks stoichiometry problems. Convert all masses to moles. Use the coefficients to relate reactants and products, then convert back to grams if needed. In real mixes, one ingredient usually runs out first. That is the limiting reagent, the reactant that is completely consumed and therefore sets the maximum amount of product that can form. You find it by converting each reactant to the moles of product it could make. The smallest answer wins, and that reactant limits the outcome. The other reactants are present in excess and will be left over once the limiting reagent is gone. Because the world is not perfectly tidy, what you actually collect is often less than what the calculation predicts. Percent yield is a clear scorecard. Percent yield equals actual yield divided by theoretical yield multiplied by 100%. If a reaction should produce 10 grams of product but you isolate 8 grams, the percent yield is 80%. Losses can come from side reactions, incomplete conversion, or a little product left behind on the glassware. Useful reminders that doing chemistry is as much technique as arithmetic. Excess reagent is simply the portion of a non-limiting reactant that remains after the limiting reagent has been used up. Once you know the limiting reagent, you can compute how much of the other reactants were actually required by the molar ratios, subtract that from what you added at the start, and the remainder is the excess. This is handy for planning. If a reagent is expensive, you do not want to toss most of it down the drain. At the heart of all this counting lies a very large number with a friendly purpose. Avogadro's number is approximately 6.022 times 10 to the power of 23 entities per mole. It tells you how many atoms, molecules, or ions are in 1 mole of anything. That number is enormous because atoms are tiny, but its job is simple. It lets chemists count unimaginably small particles using everyday amounts of material. Combine conserved atoms and charge, molar masses, limiting reagents, percent yields, and Avogadro's number, and you have the quiet arithmetic that turns a balanced equation into a reliable prediction of what and how much will appear in the beaker. An empirical formula is the simplest way to tell a chemical story. It gives the smallest whole number ratio of atoms in a compound. Glucose, for example, has the molecular formula C6H12O6, but its empirical formula reduces to CH2O, the simplest ratio of 1 to 2 to 1. The molecular formula, by contrast, tells you the actual head count. To move from empirical to molecular, you compare the empirical formula mass with the compound's molar mass. If the molar mass is, say, 3 times the empirical mass, then the molecular formula contains 3 empirical units. One elegant path to an empirical formula is combustion analysis. Burn a pure organic sample in an excess of oxygen and capture the products. All the carbon becomes carbon dioxide, and all the hydrogen becomes water. Measure the masses of carbon dioxide and water produced, convert those to moles of carbon and hydrogen, and, if oxygen is in the original sample, deduce its amount by difference from the total mass. Those mole amounts reduce to a whole number ratio, and that ratio is your empirical formula. It is chemical forensics with fire and a scale. Gases add a useful shortcut. At standard conditions of 0 degrees Celsius and 1 atmosphere, 1 mole of an ideal gas occupies about 22.4 litres. This molar volume lets you count moles from a volume directly when conditions match. Moles equal gas volume divided by 22.4 litres per mole at 0 degrees Celsius and 1 atmosphere idealised. If conditions differ, the ideal gas law steps in. Pressure times volume equals moles times the gas constant times temperature. Either way, once you have moles, the balanced equation does the rest. Titration stoichiometry is a quiet duel between measured volumes. A titrant of known concentration reacts with an analyte of unknown concentration according to a balanced equation. At the equivalence point, the mole ratio in the flask matches the stoichiometric ratio on paper. The key arithmetic is straightforward. Moles of titrant added equal concentration of titrant times volume of titrant. Use the reaction coefficients to find moles of analyte, then divide by the analyte's volume to get its concentration. Indicators or instruments tell you when the stoichiometric balance has been reached. The math tells you how much was in the sample. Gravimetric analysis trusts the scale above all. You convert the analyte into a pure insoluble compound, filter, wash, dry to constant mass and weigh. From that mass and the compound's known composition, you calculate how much analyte was present. For instance, precipitating chloride as silver chloride gives you a solid with a fixed ratio of silver to chloride. Weigh the precipitate, convert to moles of silver chloride, and the moles of chloride follow 1 to 1. It is a beautifully direct method. Fewer assumptions, more mass, and the answer appears on the balance readout. Beyond getting the right answer, stoichiometry can help judge how green a synthesis is. Atom economy asks how much of the reactant's mass ends up in the desired product rather than in byproducts. Atom economy equals mass of desired product divided by total mass of reactants, multiplied by 100%. A reaction that rearranges atoms without discarding large fragments scores high. One that lops off bulky, leaving groups scores low. High atom economy does not guarantee a perfect process. Yield, energy use, and safety still matter, but it points the way towards syntheses that waste less and use atoms wisely. Gases are the great simplifiers of chemistry, and their favourite rule is the ideal gas law. Pressure times volume equals moles, times the gas constant times temperature. Spoken plainly, pressure multiplied by volume equals the number of moles multiplied by the gas, constant multiplied by the absolute temperature. Hold any two of those steady, and the other pair must adjust. Warm a sealed balloon, and the pressure rises. Let a piston expand while temperature holds steady, and the pressure falls. It is a compact compass for how gases respond when you squeeze them, heat them, add more, or let them spread out. Mixtures of gases behave like polite roommates. Each one presses as if the others were not there. That is Dalton's law of partial pressures. The total pressure equals the sum of each gas's partial pressure. If oxygen contributes 1/3 of an atmosphere, and nitrogen contributes 2/3 of an atmosphere, the mixture sits at exactly 1 atmosphere. This additivity is why collecting a gas over water requires subtracting the water vapor's partial pressure, and why breathing air at altitude feels different. The total pressure drops, so the partial pressure of oxygen drops with it. Speed in the gas world depends on lightness. Graham's law says diffusion and effusion rates are inversely proportional to the square root of molar mass. In other words, a light gas like helium slips through a tiny pinhole, or spreads across a room faster than a heavy gas like xenon. If one gas is 4 times as massive as another, it effuses at half the rate, because the square root of 4 is 2. This simple square root relationship explains everything from why helium escapes balloons so quickly to how mass spectrometers can separate gases by their pace. Of course, real gases are not perfectly ideal. Molecules take up space and attract one another a little, and those two facts matter most at high pressures and low temperatures. When molecules have finite size, they cannot be squeezed into zero volume. When they attract, they do not hit the container walls as hard as a purely ideal model assumes. The result is deviation, pressures lower than expected near condensation, volumes larger than expected when particles are bulky, and curves that bend away from the tidy predictions of the ideal equation. To mend the model, the van der Waals equation adds 2 gentle corrections. It replaces volume with volume minus B, where B accounts for the finite size of molecules, the space unavailable because particles themselves occupy it. It also replaces pressure with pressure plus a times the square of moles divided by volume squared, where I accounts for intermolecular attractions that reduce the observed pressure. In words, adjust the volume downward for particle size, adjust the pressure upward to compensate for attractions that were stealing some push from the walls. Different gases have different A and B values because their sizes and stickiness differ. With those tweaks, predictions about real gases near liquefaction or at high compression become far more faithful. A neat way to measure how real a gas is behaving at a given moment is the compressibility factor, written as Z and defined as Z equals pressure, multiplied by volume divided by moles, multiplied by the gas constant multiplied by temperature. For an ideal gas, Z equals 1 exactly. If Z is less than 1, attractions are winning a bit and the gas is easier to compress than ideal. If Z is greater than 1, repulsions or crowding dominate, and the gas is harder to compress than ideal. Plot Z against pressure, and you get a fingerprint for each gas, a quick visual of how size and stickiness tug the behaviour away from perfection. Put these ideas together and the gas world becomes predictable without losing its charm. Pressure times volume equals moles, times the gas, constant times temperature for the broad strokes. Partial pressures add neatly in mixtures. Light molecules outrun heavy ones by a square root edge. Finite sizes and gentle attractions bend the rules. Van der Waals parameters A and B nudge the math back to reality. And the compressibility factor Z keeps score on how close you are to the ideal. All of it is the same story told from different angles. Countless tiny particles moving fast, colliding often, and, despite their chaos, obeying a handful of beautifully simple relationships. Viscosity is how stubborn a liquid is when asked to move. Honey flows slowly because its molecules cling to one another with strong intermolecular forces, and often tangle due to long chains. Water glides more easily because its hydrogen bonds, though numerous, are constantly breaking and reforming, allowing molecules to slip past one another. Raise the temperature and viscosity usually falls. Heat jostles molecules harder, loosening their grip and making the liquid less resistant to motion. Add stronger attractions, more hydrogen bonding, more polarity, longer chains, and viscosity rises, turning a pour into a leisurely stroll. Every liquid also shares space with its own invisible vapour, and the push from that vapour has a name: vapour pressure. In a closed container, molecules at the surface occasionally escape into the gas phase, while gas molecules return to the liquid, and at equilibrium those rates match. Stronger intermolecular forces hold molecules down more firmly, so fewer escape, and the vapour pressure drops. That is why a pan of ethanol evaporates more quickly than an equal pan of water. Ethanol's weaker hydrogen bonding lets more molecules leap into the air, building a higher vapour pressure at the same temperature. Boiling is simply the moment a liquid's vapour pressure equals the external pressure. At that point, bubbles of vapour can form not just at the surface, but throughout the liquid, because the vapour inside the bubbles is no longer crushed by the surrounding pressure. Lower the external pressure by climbing a mountain or using a vacuum, and the boiling point falls. Water boils at lower temperatures at high altitude, which is why recipes sometimes need longer cooking times on mountain tops. Increase the pressure, as in a pressure cooker, and the boiling point rises, trapping heat in the pot and cooking food faster. It all hinges on that equality, vapour pressure meeting the pressure outside. Solids come in two broad flavours. Crystalline solids have atoms, ions, or molecules arranged in repeating orderly patterns that extend in all directions. Salt crystals, quartz, and metals fit this description. Their repeating lattices explain sharp melting points, and often well-defined faces and cleavage planes. Amorphous solids, by contrast, lack long-range order. Glass and many plastics are frozen into place without settling into a repeating pattern. They soften over a range of temperatures rather than melting sharply, and their properties can vary subtly with how they were cooled and processed. Order or no order, the difference shapes how solids fracture, conduct heat, and interact with light. Some elements can wear different structural outfits called allotropes, and carbon is the celebrity example. Arrange carbon atoms into a rigid three-dimensional network with each atom bonded to 4 neighbours, and you have diamond, extremely hard, optically brilliant, and an outstanding conductor of heat but not electricity. Arrange them in flat hexagonal sheets with each atom bonded to 3 neighbours, and you have graphite, soft, slippery, and electrically conductive along the planes thanks to delocalized pi electrons. Same element, same atoms, entirely different properties because bonding and geometry change. Allotropy appears elsewhere too. Oxygen can be diatomic O2 or triatomic ozone O3. But carbon's contrast between diamond and graphite is a vivid reminder that structure dictates behaviour. Not every solid needs a liquid phase to escape into a gas. Sublimation is the direct transition from solid to gas without a liquid middle step. Dry ice, which is solid carbon dioxide, is famous for this. At ordinary atmospheric pressure, it does not melt. It simply turns into carbon dioxide gas, rolling off as a cold fog. Naphthalene in mothballs and iodine crystals will also slowly sublime at room temperature, releasing a telltale smell of violet vapour. Whether a substance sublimates easily depends on the shape of its phase diagram. If the triple point, where solid, liquid and gas coexist, sits above everyday pressures, the material can skip the liquid state entirely under normal conditions. Put these pieces together and the behaviour of liquids and solids becomes intuitive. Stronger attractions knit liquids into more viscous, higher boiling, lower vapour pressure states. External pressure sets the bar for boiling by deciding when bubbles can stand their ground. Order versus disorder in solids separates sharp melting crystals from softening glasses. Allotropes remind us that the same atoms, arranged differently, make new worlds of properties. And sublimation shows that phase changes are about energy and pressure, not a compulsory tour through solid, then liquid, then gas. When you watch a raindrop bead on a waxed leaf, see a kettle boil sooner at sea level than on a mountain, or feel the slick trace of graphite from a pencil, you are seeing these quiet principles in motion. Concentration comes in two flavours that sound similar but measure different things. Molarity counts how many moles of solute are dissolved per litre of the final solution. Volume on the bottom, so it shifts if temperature or mixing changes the volume. Molality counts how many moles of solute are dissolved per kilogram of solvent. Mass on the bottom, so it stays steady when things warm up or cool down. If you want to describe how strong your lemonade is in a beaker that might expand a little with heat, molarity is convenient. If you're tracking how a solution behaves as temperature changes, say in freezing point experiments, molality is the steadier yardstick. Some dissolved substances carry electricity from one side of a solution to the other. These are electrolytes. Strong electrolytes, such as sodium chloride or nitric acid, dissociate completely into ions in water, so the solution conducts very well. Weak electrolytes, like acetic acid or ammonia, dissociate only partially, establishing an equilibrium between ions and intact molecules. Their solutions conduct but more modestly. Non-electrolytes such as sugar or ethanol dissolve without forming ions at all, so they keep the lights off even when well mixed. In practical terms, the number of mobile ions, not just the amount of stuff dissolved, decides how brightly the conductivity bulb glows. Temperature gently tilts the balance of what dissolves. For many ionic and molecular solids in water, solubility increases as temperature rises. Add heat, and the lattice gives way more easily while water can better accommodate the guests. That is why a spoonful of sugar disappears faster in hot tea than in iced tea. Gases behave the other way around. Warm water holds less dissolved gas because gas molecules gain energy and prefer the freedom of the air. That is why a warm soda goes flat faster, and why fish thrive in cooler streams that carry more dissolved oxygen. A tidy relationship links gas solubility to the pressure of that gas above the liquid. This is Henry's law. The solubility of a gas is proportional to its partial pressure over the liquid. Double the pressure of carbon dioxide above a beverage during bottling, and roughly double the amount that dissolves. Pop the cap, the pressure above the liquid drops, and the excess gas escapes until a new balance is reached. The same principle underlies scuba diving guidelines. Breathing compressed air increases dissolved nitrogen in the blood. Ascend slowly, and the pressure drops gradually, letting nitrogen leave solution without forming harmful bubbles. When ions do dissolve in water, the surrounding liquid does not ignore them, it organises. Hydration shells form as water molecules orient themselves round each ion. The partially negative oxygen end faces toward a positive ion like sodium, while the partially positive hydrogen ends point toward a negative ion like chloride. Layers of water align, the first shell tightly held, the next more loosely structured. These cages stabilize ions, lower the energy cost of pulling them from a crystal, and help them move smoothly through the liquid. In many biochemical reactions, these hydration layers are as important as the ions themselves, steering how molecules meet and react. All of this rests on a rule of thumb with plenty of predictive power, like dissolves like. Polar solvents with uneven charge distributions are good at stabilizing polar or ionic solutes through dipole interactions and ion-dipole attractions. Water, the archetypal polar solvent, dissolves salts and sugars with ease. Non-polar solvents, whose molecules share electrons more evenly, are better hosts for non-polar solutes that rely on dispersion forces. Oils mix with hexane, waxes with toluene. Try to cross the divide and the party falls flat. Oil beads on water because the strong water-water hydrogen bonds would have to break to make room, and there is too little payback from weak oil-water interactions. Add an amphiphile like soap, and it can broker peace by offering a hydrophilic head to water and a hydrophobic tail to the oil, but that is a story about interfaces rather than true solubility. Together these ideas turn dissolving from a mystery into a set of gentle expectations. Choose molarity when volumes matter, and molality when temperatures change. Expect strong electrolytes to light up a conductivity probe and weak ones to glow dimly. Warm water to dissolve more solid, cool it to keep more gas. Raise the gas pressure to load more into a liquid, lower it to let bubbles out. Picture ions wrapped in aligned water molecules, gliding as hydrated guests, and when in doubt, remember the simple map: polar with polar, non-polar with non-polar, water for salt and sugar, hexane for grease and wax. Some solution effects care only about head count, not personality. These are colligative properties, behaviours that depend on how many particles are dissolved, not what those particles are. Add any non-volatile solute to a solvent and you change its boiling point, its freezing point, its vapour pressure, and the pressure needed to push water through a membrane. Sugar, salt, or a perfectly harmless polymer. For these properties, the key is simply how many independent pieces the solute provides per unit of solvent. Start with boiling point elevation. Dissolved particles make it harder for solvent molecules to escape into the vapour, so you must heat a little more to make bubbles form throughout the liquid. The size of the effect is given by delta T sub B equals the abelioscopic constant times molality, times the Van 't Hoff factor. In words, the boiling point increase equals K sub B multiplied by the solution's molality multiplied by I, where I counts how many particles a solute effectively produces. This is why a pan of salty water boils at a slightly higher temperature than pure water. The solute crowds the surface and lowers the solvent's escaping tendency, nudging the boiling point upward by a predictable amount. Flip the situation to freezing, and you get the mirror image: freezing point depression. Dissolved particles disrupt the orderly crystal that a solvent wants to form, so the liquid must be cooled further to lock into a solid. The rule is delta T sub F equals the cryoscopic constant times molality times the Van 't Hoff factor. In words, the drop in freezing point equals K sub F multiplied by molality multiplied by I. Road crews spread salt in winter because the brine that forms has a lower freezing point than pure water, preventing ice from reforming until the temperature falls farther. Ethylene glycol in car radiators works the same way, lowering the freezing point and raising the boiling point. widening the safe liquid range. A third colligative property is osmotic pressure, the pressure needed to stop solvent from flowing through a semi-permeable membrane into a more concentrated solution. The relationship is compact. P equals molarity times the gas constant times temperature. In words, osmotic pressure equals M multiplied by R multiplied by absolute temperature. This matters in biology. Red blood cells must be bathed in an isotonic solution so that water does not rush in and swell them or rush out and shrivel them. It also matters in technology. Reverse osmosis water purifiers use pressures greater than pi to push water back through a membrane, leaving salts behind. All of these effects share a common cause. Non-volatile solutes lower the solvent's vapor pressure, a principle captured by Raoult's law. In an ideal solution, the partial pressure of the solvent equals its mole fraction in the liquid multiplied by its pure vapor pressure. Less solvent at the surface means fewer molecules escaping per second, which shows up as a lower vapor pressure. From that single change, the boiling point shifts up, the freezing point shifts down, and a pressure is needed to stop osmosis. Three faces of the same underlying reduction in escaping tendency. Electrolytes add an extra twist by splitting into multiple ions when they dissolve, effectively increasing the particle count. That is the Van 't Hoff factor again. Sodium chloride ideally gives 2 particles per formula unit, sodium plus 1 and chloride minus 1, so I is about 2 under dilute ideal conditions. Calcium chloride ideally gives 3, calcium plus 2 and 2 chloride minus 1, so I is about 3. A non-electrolyte like glucose does not dissociate, so I is about 1. This is why, mole for mole, calcium chloride depresses the freezing point of water more than table sugar does, not because it is saltier, but because it creates more dissolved pieces that interfere with ice formation. Pull the threads together and colligative properties become a practical toolkit. Need to raise a boiling point or protect against freezing? Choose a solar and calculate with delta T sub B equals K sub B times molality times I, and delta T sub F equals K sub F times molality times I. Need to predict water flow across a membrane? Use pi equals MRT. Expect vapor pressure to fall in proportion to how much solute you add, by Raoult's law. And remember that electrolytes punch above their molar weight because they split, boosting the effective particle count. For colligative properties, chemistry's mantra is simple. Count the particles, and the rest will follow. Thermodynamics begins with a promise that the universe always keeps. Energy is conserved. The first law says the change in a system's internal energy equals heat plus work. Put in words for an easy read. Delta U equals Q plus W. If the system absorbs heat, Q is positive. If the surroundings do work on the system, W is positive. If the system itself does work on the surroundings, pushing back a piston or expanding into a vacuum, W becomes negative because energy leaves the system. Nothing appears from nowhere. Nothing vanishes without a trace. Energy merely switches pockets. A closely related idea is enthalpy, a convenient bookkeeper for processes at constant pressure, which, in open beakers and the atmosphere, is most of everyday chemistry. The enthalpy change approximates the heat flow when pressure does not change. Exothermic reactions release heat to the surroundings. Endothermic reactions absorb it from the surroundings. Touch a flask that is getting warmer and you're feeling an exothermic process pay out energy. Touch one that chills your fingers and you have an endothermic process drawing heat in. Enthalpy is the signpost. Negative for exothermic, positive for endothermic, always telling you which way the thermal tide is flowing. To compare substances on a fair field, chemists use standard enthalpies of formation. This is defined as the enthalpy change when exactly 1 mole of a compound forms from its pure elements in their standard states at a chosen reference, typically 1 bar pressure and a specified temperature such as 25 degrees Celsius. The elements in their standard states are assigned 0 by convention. Graphite for carbon, diatomic oxygen gas for oxygen, diatomic hydrogen gas for hydrogen. From those zeros, the formation values let you build up the enthalpy of almost any reaction by adding products and subtracting reactants. That build-up by adding is formalized by Hess's law. If a reaction can be written as the sum of several steps, the overall enthalpy change is the sum of the enthalpy changes of those steps. Energy is a state function. It cares about the start and finish, not the path you took. So you are free to flip equations, changing the sign of delta H, multiply them, scaling delta H, and add them, just as long as everything cancels properly. It is like assembling a jigsaw puzzle of known heats to reveal the enthalpy of a reaction you cannot measure directly. Measuring heat in practice is the art of calorimetry. You place a reaction in a well-insulated container with a known heat capacity and watch the temperature change. The absorbed or released heat equals the effective heat capacity multiplied by the temperature change with attention to the sign. In a coffee cup calorimeter at constant pressure, that measured heat maps directly onto an enthalpy change. In a sturdier bomb calorimeter at constant volume, it maps onto the change in internal energy. Either way, a thermometer becomes a translator between molecular events and numbers on a page. Finally, work has a clear mechanical meaning in many chemical settings. Pressure-volume work during expansion or compression. When a gas expands against an external pressure, the system spends energy to push the surroundings back. The relationship is compact and worth saying out loud. mu equals negative pressure external multiplied by delta V. If the volume increases, delta V is positive and W is negative. The system did work on the surroundings. If the volume shrinks under an external squeeze, delta V is negative and W is positive. Work was done on the system. Pair this with delta U equals Q plus W, and you can follow the energy as heat flows and pistons move, confident that the tally will always come out even. Entropy is a measure of how energy spreads out and how many ways a system can arrange itself. When energy is more dispersed and more microstates are available, entropy is higher. Many natural changes are nudged forward because they scatter energy more widely. A drop of dye diffuses through water, a hot object cools to match the room, a gas expands to fill a container. None of these need a push once started. Entropy does not mean messy so much as more ways to be, and the universe tends to prefer the options with more room to breathe. This preference is captured by the second law of thermodynamics. For any spontaneous process, the entropy of the universe increases. In everyday terms, the combined entropy of the system plus the surroundings must rise for a change to occur on its own. You can certainly make a local pocket of lower entropy. A freezer turns liquid water into more ordered ice, but only by dumping heat into the surroundings and increasing their entropy even more. Spontaneity is not a moral judgment. It is an accounting rule that says the grand total of spread outness must go up. To make predictions in the lab, chemists use a quantity that braids energy and entropy into a single score: Gibbs free energy. The defining relationship is neat enough to say out loud. Delta G equals delta H minus temperature times delta S. Here, delta H is the enthalpy change, the heat flow at constant pressure, and delta S is the entropy change. Temperature acts as the exchange rate between energy and entropy, measured on an absolute scale. This simple combination weighs the tug of heat against the pull of disorder and declares a winner under the conditions you care about. The sign of delta G tells you whether a process is thermodynamically favourable under the specified conditions. If delta G is negative, the change can proceed spontaneously. If delta G is positive, it will not proceed without work being supplied, If delta G is 0, the change is at equilibrium exactly 0. The system sits at equilibrium. A negative delta G does not promise speed. A diamond will eventually turn into graphite because the change in free energy is favourable, but the kinetic barrier is enormous, so diamonds endure. Thermodynamics sets the destination. Kinetics decides how quickly you arrive. Temperature can tip the balance because it multiplies the entropy term. An endothermic reaction, one with a positive delta H, may still be spontaneous if it produces a large enough increase in entropy, making the term temperature times delta S big and positive. Then delta H minus temperature times delta S becomes negative above some threshold temperature. The dissolution of certain salts is a familiar example. They cool the water as they dissolve, endothermic, yet the strong increase in entropy from ions and water mixing can carry the day at ordinary temperatures. By adjusting temperature, you dial how much weight entropy gets in the decision. At equilibrium, delta G equals 0, and the forward and reverse processes balance exactly. Molecules still react. They simply do so at equal rates in both directions, so the macroscopic amounts remain steady. This special point links free energy to the equilibrium constant through a concise relation. Delta G standard equals negative R times T times the natural log of K. In words, the standard free energy change equals negative the gas, constant times temperature, times the natural logarithm of the equilibrium constant. Large positive K means products are favoured, and delta G standard is negative. Small k means reactants are favoured, and delta G standard is positive. Shift the temperature, and both k and the favoured side can shift with it. These ideas shape everything from why ice melts on a warm day to why ATP hydrolysis can drive cellular work. When energy disperses and arrangements multiply, entropy rises. When the weighted sum of energy and entropy, delta G, comes out negative, a change becomes thermodynamically favourable. Heat may help or hinder, and temperature decides how loudly entropy speaks. And when the score reaches exactly 0, the system finds its quiet balance, not frozen in place, but humming with equal and opposite motions that, on average, cancel. A stillness woven from countless tiny rearrangements. At the heart of every chemical reaction is a trade. Some bonds are broken, some new bonds are formed, and energy is the currency that balances the books. Breaking a chemical bond always costs energy. You must pull atoms apart against their mutual attraction. Forming a new bond releases energy. Atoms fall into a lower, more comfortable arrangement and give back the excess. The overall reaction enthalpy is the sum of those costs and paybacks. If the bonds you form are, on balance, stronger than the ones you break, the reaction is exothermic and releases heat. If the bonds you form are weaker, the reaction is endothermic and soaks up heat. Think of it as renovating a house. Demolition takes effort, but installing sturdier beams can leave you with a stronger structure and some energy credit returned to the surroundings. When exact thermochemical data are missing, chemists reach for a very practical toolkit: average bond enthalpies. These are typical energies for breaking particular bonds: carbon-hydrogen, carbon-carbon, carbon-oxygen, oxygen-hydrogen, averaged over many molecules. They're not perfect for every context, but they offer quick, surprisingly good estimates. The arithmetic goes like this: add up the energies to break all the bonds in the reactants, then subtract the energies released when making all the bonds in the products. If the result is negative, the reaction is exothermic. If positive, endothermic. It is a back-of-the-envelope way to forecast whether a process will warm your beaker or cool it. Combustion showcases the exothermic side at full brightness. Burn a hydrocarbon in oxygen, and you convert relatively weaker carbon-carbon and carbon-hydrogen bonds into very strong carbon-oxygen bonds in carbon dioxide and oxygen-hydrogen bonds in water. Those product bonds are among the most stable in chemistry, so the net result is a large release of heat and often light. Flames are the visible proof. This is why fuels ranging from methane to octane are so energy-rich. They are preloaded with bonds that, when rearranged into carbon dioxide and water, pay out a substantial enthalpy dividend. To track how substances respond to added heat, we use specific heat capacity, the energy required to raise 1 gram of a substance by 1 degree Celsius. Water's specific heat is notably high, which is why oceans moderate coastal climates and why a mug of tea stays warm far longer than the same mass of air would. Metals typically have much lower specific heats, so they warm quickly and cool quickly. In calorimetry, this property turns temperature changes into precise heat measurements. Heat equals mass multiplied by specific heat, multiplied by the change in temperature. Not all heating increases temperature. During a phase change, energy goes into rearranging the positions of molecules rather than speeding them up. As a result, the temperature holds steady while the system absorbs or releases latent heat. When ice melts at 0 degrees Celsius, added heat breaks hydrogen bond organization without raising the temperature until every last crystal has liquefied. When water boils at 100 degrees Celsius at 1 atmosphere, heat goes into freeing molecules from the liquid, building vapor without budging the thermometer until the last drop is gone. Only after the phase change finishes does the temperature begin to climb again. A heating curve ties these ideas together in a picture. Slanted lines where temperature rises as heat increases the kinetic energy, and flat plateaus where temperature pauses while the substance changes phase. Starting with ice below 0 degrees Celsius, you warm to 0 degrees Celsius, a slanted climb. Melt at 0 degrees Celsius, a flat segment. Warm the liquid water to 100 degrees Celsius, another slanted climb. Boil at 100 degrees Celsius, a second flat segment, and then heat the steam above 100 degrees Celsius, a final slanted climb. Each slope depends on specific heat. Each plateau depends on latent heat. The shape of the curve is a fingerprint of the substance's capacity to store and transform energy. Put together, thermochemistry becomes a story you can read at a glance. Bond breaking absorbs energy. Bond forming releases energy. Combustion is powerfully exothermic because it trades up to very strong bonds. Specific heat capacity sets how sharply temperatures respond to added heat. Phase changes stall temperature, while latent heat does structural work. And a heating curve maps the journey with climbs and plateaus. Once you see reactions as careful exchanges of bond energy, and phases as rearrangements that temporarily borrow the thermometer's needle, the warmth of a flame, the cool of an evaporating mist, and the flat calm of boiling water all make elegant quantitative sense. Reaction rate is simply how fast concentration changes with time, how quickly reactants disappear or products appear. Stirring, temperature, surface area, catalysts, and even the container can nudge that speed up or down, and the underlying pathway, the mechanism, matters just as much. Two reactions with the same overall equation can proceed at very different paces if their molecular dance steps differ. Rate is the slope of concentration versus time. Steep means fast, gentle means slow. To connect rate with amounts, chemistry uses a rate law, an equation that relates the reaction rate to reactant concentrations, each raised to a reaction order. In its simplest form, rate equals Ks times the concentration of A to the power A times the concentration of B to the power N. Here, K is the rate constant under the given conditions, while M and N are the empirical orders determined by experiment, not necessarily by the stoichiometric coefficients. Double the concentration of A, And if m is 1, the rate doubles. If m is 2, the rate quadruples. The exponents tell you how sensitively the reaction responds to concentration changes. Temperature leans on the rate constant through the Arrhenius equation, which says K equals A multiplied by the exponential of negative activation energy divided by R times T. In words, the rate constant equals the pre-exponential factor times ER to the power of negative E sub A over RT. As temperature T rises, more molecules carry enough energy to cross the activation barrier E sub A, so K grows and the reaction speeds up. Even modest warming can have a big effect because the exponential term amplifies the change. This is why food spoils faster on a warm day, and why cold slows biochemical processes. Catalysts give molecules a gentler hill to climb. A catalyst provides an alternative pathway with a lower activation energy, so more collisions succeed at the same temperature. Crucially, the catalyst is not consumed overall. It participates in the steps, and then is regenerated by the end. Lowering E sub A increases the rate constant K according to the Arrhenius relation, which increases the rate for the same concentrations. A catalyst does not change the equilibrium position, only how quickly equilibrium is reached, because it accelerates both the forward and reverse reactions. Beneath the overall equation lies the mechanism, a sequence of elementary steps that actually occur. Each step has its own molecularity, unimolecular, bimolecular, and its own rate law. Usually one step is slower than the rest and acts as the bottleneck, the rate-determining step. The overall rate law often reflects the molecularity and participants of that slowest step, possibly modified by steady-state or pre-equilibrium relationships for intermediates. Change the bottleneck and you change the observed kinetics, even if the initial and final substances look the same on paper. Different overall orders leave distinct time signatures, the integrated rate laws and the way half-life behaves. Zero-order kinetics. The rate is constant and independent of concentration. The integrated law is concentration of A at time T equals concentration of A at time 0 minus K times T. The plot of concentration versus time is a straight line. The half-life equals the initial concentration divided by 2K. As the reaction proceeds, the half-life gets shorter because it depends on the starting concentration. First-order kinetics. The rate is proportional to concentration. The integrated law is the natural log of the concentration of A at time T equals the natural log of the concentration of A at time 0 minus K times T. The plot of natural log of concentration versus time is a straight line. The half-life equals the natural log of 2 divided by K, the elegant hallmark that the half-life is constant, independent of how much you started with. Radioactive decay and many simple decompositions follow this pattern. Second-order kinetics. The rate is proportional to the square of one concentration, or to the product of two concentrations. For the simple case where the rate equals K times the concentration of S squared, the integrated law is 1 over the concentration of A at time T equals 1 over the concentration of A at time 0 plus K times T. The plot of the reciprocal concentration versus time is a straight line. The half-life equals 1 divided by K times the initial concentration. As the starting amount decreases, the half-life grows longer. These mathematical fingerprints, straight lines on the right plots and characteristic half-lives, let you diagnose reaction order from experimental data, measure concentration over time, try the appropriate transforms, and the linear one reveals the kinetics. Pair that with temperature dependence from the Arrhenius equation. Plot the natural log of K versus 1 over T, and the slope gives negative E sub A over R, and you can extract both the mechanism's kinetic form and its energy barrier. Tie it all together, and kinetics becomes a practical playbook. Rate is the pace. The rate law tells how the pace depends on concentration. The Arrhenius equation shows how temperature tunes the pace. A catalyst lowers the hill without moving the finish line. The mechanism explains why the observed law looks the way it does, and the order-specific integrated laws and half-lives turn raw time concentration data into clear parameters. From rust creeping across iron to enzymes knitting life's molecules at body temperature, the same principles govern how fast chemistry happens. Reactions happen when molecules actually meet, and not every meeting counts. Collision theory says two things must be true at the same time. The collision must carry enough energy to overcome the activation barrier, and the molecules must be oriented so that the right atoms can form or break bonds. Imagine two dancers trying a complicated lift. They need momentum, and their hands must find the right grip. Plenty of collisions are glancing blows with the wrong angle or too little energy. Only a fraction are productive. That fraction grows with temperature, more fast movers, and with the steric factor, a measure of how often orientations are favourable. Bulky groups can lower that factor by getting in the way, even if the energy is there. Transition state theory zooms in on the split second when a reaction teeters at the top of its energy hill. At this peak sits the activated complex, not quite reactants, not quite products, a high-energy, fleeting arrangement in which bonds are in the process of stretching and forming. Crossing that saddle point leads downhill to products. Sliding back returns to reactants. The theory links the rate to how frequently molecules form this activated complex, and how likely it is to proceed forward. It is a more detailed version of collision theory's simple picture. Instead of counting only successful hits, it imagines a bottleneck at the top of the barrier and asks how quickly traffic can pass through. Nature's masterclass in catalysis is the enzyme. Enzymes speed reactions by stabilizing the transition state, far more than they stabilize either reactants or products. They do this with exquisite specificity. Binding pockets place substrates in just the right orientation. Charged or polar amino acids provide complementary interactions. Sometimes a temporary covalent bond forms to guide electrons along the shortest path. The old lock and key image captures specificity, while induced fit adds the idea that the protein flexes to embrace the substrate tightly, especially in the transition state geometry. Lower the activation energy, and, by the Arrhenius logic, the rate constant rises dramatically, often by factors of 1,000,000 or more, yet the enzyme emerges unchanged, ready for another cycle. Catalysis can also happen on solid surfaces, heterogeneous catalysis, where reagents from a gas or liquid phase react at the interface. The choreography usually has 4 steps: adsorption of reactants onto the surface, diffusion to special sites, the surface reaction itself, often involving bond breaking and making aided by the surface's electrons, and desorption of products. Active sites, particular arrangements of atoms, steps, edges, or defects, do most of the work because they bind just strongly enough to hold molecules, but not so tightly that products cannot leave. Industrial chemistry runs on this concept. Iron catalysts for ammonia synthesis, platinum and rhodium in catalytic converters, nickel for hydrogenation. Poisons such as sulfur or lead bind too strongly to active sites and block them, throttling the rate until the surface is cleaned or replaced. Some reactions gather speed as they go because one of the products is itself a catalyst. That self-help loop is autocatalysis. Early on, the rate is modest. As more product accumulates, it accelerates, often giving a characteristic S-shaped, sigmoidal progress curve. Acid-catalyzed ester hydrolysis can show this when acid is produced in the mechanism. Certain redox systems do as well. Autocatalysis crops up in biology in self-assembly too. where a small amount of a folded structure promotes more of the same structure to form. A molecular version of success breeds success. Not every helper speeds things up. Some guests slow the party. Inhibition reduces reaction rate by interfering with the catalytic pathway or by diverting traffic down less efficient routes. In enzyme kinetics, competitive inhibitors resemble the substrate and occupy the active site, raising the apparent K sub m because more substrate is needed to achieve the same rate. Increase the substrate enough, and you can outcompete them. Non-competitive inhibitors bind elsewhere, an allosteric site, and lower the maximum rate by reducing the number or effectiveness of working enzymes. More substrate does not solve this. Uncompetitive inhibitors bind only to the enzyme substrate complex, commonly in multi-step pathways, altering both K sub m and V max. Outside biochemistry, inhibitors can be simple surface poisons in heterogeneous catalysis, coating active sites, or radical scavengers in chain reactions, mopping up reactive intermediates and halting propagation. Across all these cases, the storyline is consistent. Molecules must meet with the right energy and geometry. The crucial high-energy arrangement at the top is the transition state. Catalysts, especially enzymes, work by making that top lower and easier to reach, either in solution or on a surface. Feedback can make a reaction accelerate itself through autocatalysis, and inhibitors apply the brakes by blocking routes or disabling the most efficient steps. Once you start to see rates as a balance between pathways opened, pathways blocked, and barriers reshaped, the kinetics of rusting metal, ripening fruit, refining fuel, and replicating DNA all follow the same elegant logic. Equilibrium is chemistry's version of a truce, a point where the push from reactants to products is exactly balanced by the pullback again. The number that captures this balance is the equilibrium constant, K, defined as the ratio of product activities to reactant activities when the system has settled into its steady state. In words, K equals the activity of products each raised to their stoichiometric powers divided by the activity of reactants each raised to their stoichiometric powers. Activities are the properly corrected effective concentrations, so in dilute solutions you can often think of them as concentrations, and in gases you often use partial pressures. The beauty is that one compact number tells you how the scales tip when everything stops changing overall. Red K like a compass. A large K means the reaction mixture, when left alone, will be composed mostly of products. The balance point lies far to the product side. A small K means the mixture rests mostly with reactants. The balance point lies to the left. K does not tell you how quickly you arrive, that is kinetics, but it does tell you the destination. Whisper large K and think products favoured. Whisper small k and think reactants favoured. Before the system reaches that truce, you can ask which way it is leaning right now by calculating the reaction quotient, Q, using the same ratio of activities that define K, but with the current, not yet equilibrium amounts. If Q is less than K, the mixture has too few products relative to equilibrium, so the forward reaction is favoured until Q grows to match K. If Q is greater than K, there are too many products, and the reverse reaction will dominate until Q falls to K. If Q equals K, you're already at equilibrium. This simple comparison, Q versus K, is the traffic sign that tells you whether the reaction will roll forward, slip backward, or sit quietly. Equilibrium may sound like stasis, but it is anything but. It is dynamic, a constant exchange at the molecular level. At the balance point, the forward and reverse reaction rates are equal. Molecules still collide, bonds still break and form, and intermediates still flicker in and out of existence. What stops changing is the macroscopic composition. For every product molecule formed by the forward reaction, another product molecule returns to reactants by the reverse reaction. Imagine a busy bridge with equal traffic in both directions. The total number of cars on each side stays the same even though cars never stop moving. When writing K, not every species gets a seat in the ratio. Pure solids and pure liquids do not appear explicitly because their activities are defined as one by convention. Their effective concentration does not change in a way that matters for the equilibrium calculation. A block of solid has the same activity regardless of how big the block is, as long as some solid is present. That is why, for a heterogeneous equilibrium like calcium carbonate solid in equilibrium with calcium oxide solid plus carbon dioxide gas, the equilibrium constant depends only on the activity, often partial pressure, of carbon dioxide gas. The solids are part of the story but do not clutter the equation. Stoichiometry, those coefficients in the balanced equation, sets the exponents in K, and changing the way you write the reaction changes K in a predictable way. If you double every coefficient in the balanced equation, you square K. If you halve every coefficient, you take the square root of K. If you reverse the reaction, you invert K, 1 over K. This is not a trick, it is bookkeeping. K is built from activities raised to powers that mirror the coefficients, so scaling the equation simply scales the powers and therefore the value of K. The chemical reality has not changed, only the way you've chosen to write it, and K follows those choices with precise algebra. All of this makes equilibrium a remarkably practical tool. Measure concentrations or partial pressures at equilibrium once, and you can compute K. With K in hand, you can predict how an arbitrary starting mixture will shift by checking Q, determine which side is favoured under given conditions, and decide whether removing a product will draw the reaction forward or whether adding a reactant will do the same. You can even connect K to thermodynamics through the relation that the standard free energy change equals negative, the gas constant times temperature times the natural logarithm of K, translating a balance of forces picture into an energy landscape. In the lab and in life, equilibrium is not the absence of change. It is the quiet of equal and opposite changes, perfectly matched. Le Chatelier's principle offers a simple intuition. When a system at equilibrium is disturbed, it responds by shifting in the direction that counteracts the disturbance. Imagine the equilibrium as a balanced seesaw. If you push down on one side, the system leans the other way to restore balance. This does not change the equilibrium constant at a fixed temperature. It only changes the composition needed to satisfy that constant under the new conditions. One of the cleanest disturbances is to add more reactant. If you pour in extra reactant, the reaction shifts forward to use it up, forming more product until the ratio of products to reactants again matches the equilibrium constant. Likewise, removing product also drives the reaction forward because the system tries to replace what was taken. In the classic ammonia synthesis, written as nitrogen gas plus 3 hydrogen gas yields 2 ammonia. Adding nitrogen gas or hydrogen gas pushes the system toward more ammonia, and continuously removing ammonia as it forms keeps pulling the reaction forward. Pressure changes matter for reactions involving gases. If you increase the pressure by decreasing the volume, the equilibrium shifts toward the side with fewer moles of gas, reducing the total number of gas particles and hence the pressure. In the same ammonia example, nitrogen gas plus 3 hydrogen gas yields 2 ammonia. The left side has 4 moles of gas per stoichiometric set, while the right has 2 moles. Raising the pressure favours ammonia formation. Lowering the pressure favours the separate gases. This effect does not apply if the total gas moles are the same on both sides. Temperature nudges equilibrium through the reaction's heat character. Treat heat like a reactant for endothermic reactions, and like a product for exothermic reactions. If a reaction is endothermic in the forward direction, warming the system adds heat reactant, shifting the equilibrium forward. Cooling shifts it backward. If a reaction is exothermic in the forward direction, heating adds heat product, shifting the equilibrium backward. Cooling pulls it forward. Temperature changes also alter the value of the equilibrium constant itself, because the constant depends on temperature through the underlying thermodynamics. Catalysts often seem magical because they speed up reactions, but in equilibrium terms they're careful not to pick favourites. A catalyst lowers the activation energy for both the forward and reverse reactions by the same energetic pathway adjustment. The system reaches equilibrium faster, but the final position, the ratio of products to reactants at that temperature, is unchanged. Catalysts help with the journey, not the destination. In solutions, dilution is another lever. Add solvent, and all concentrations drop. The system responds by shifting toward the side with more dissolved particles to partially restore concentration. For a simple association reaction where two dissolved species form one product, dilution drives the equilibrium backward toward more, smaller particles. For a dissociation where one species splits into two or more ions, dilution drives the equilibrium forward, favouring the side with more pieces. In short, more volume favours more particles. Put together, Le Chatelier's guidance becomes a practical checklist. Add reactant or remove product to pull forward. Squeeze the volume to favour the side with fewer gas moles. Release it to favour more. Warm endothermic systems to make products. Cool exothermic ones to make products. Use catalysts to arrive at equilibrium sooner, knowing they will not move the finish line. Dilute to favour the side with more dissolved particles. With these instincts, you can often predict the direction of shift at a glance. A quiet confidence that comes from seeing equilibrium as a balance that always leans against your push. Acids and bases can be defined in several useful ways, each one shining a light on different chemical situations. In the Arrhenius view, perfect for aqueous solutions, an acid is a substance that increases the concentration of hydronium ions in water, while a base increases the concentration of hydroxide ions. Think of hydrogen chloride gas meeting water. Hydrogen chloride plus water yields hydronium ion plus chloride ion. Drop sodium hydroxide pellets into water and they dissociate to give sodium ion plus hydroxide ion. This lens is simple and powerful whenever water is the stage. Move to the Brønsted-Lowry definition, and the idea stretches beyond water with a neat symmetry. Acids donate protons and bases accept protons. Every acid has a conjugate base left behind after donation. Every base has a conjugate acid after acceptance. Ammonia and water is a classic example. Ammonia plus water yields ammonium ion plus hydroxide ion. Here, ammonia is the base, it accepts a proton, and water acts as the acid, it donates a proton. The products form a conjugate pair. Ammonium is the conjugate acid of ammonia, and hydroxide is the conjugate base of water. Once you start spotting these pairs, acid-base chemistry becomes a series of tidy handoffs. One molecule lets go, another catches. Widen the circle once more with Lewis acids and bases, which focus on electrons rather than protons. A Lewis acid accepts an electron pair, a Lewis base donates an electron pair. This definition sweeps in reactions where no protons move at all. Boron trifluoride with an empty orbital is a Lewis acid. Ammonia with a lone pair is a Lewis base. Put them together and you form a coordinate bond. Boron trifluoride plus ammonia yields a Lewis adduct in which the nitrogen's pair is shared with boron. Metal ions behave similarly. A copper 2+ ion is a Lewis acid that binds electron pair donors such as water, ammonia or chloride to form coordination complexes. With the Lewis idea, acid-base chemistry becomes a map of electron pair traffic. Some substances play for both teams depending on the surroundings. They are amphoteric. Water is the most familiar. In the presence of a stronger base, it donates a proton, acting as an acid, and next to a stronger acid, it accepts a proton, acting as a base. Aluminum hydroxide and zinc oxide also show amphoteric behavior in solution, dissolving in strong acids and in strong bases via different reactions. Bicarbonate is another everyday example, acting as a base when it grabs a proton to become carbonic acid, and acting as an acid when it donates a proton to become carbonate. Context decides which role wins. Acids come in different strengths, and strength here means how completely the acid donates protons to the solvent. Strong acids like hydrochloric acid, nitric acid, and the first proton of sulfuric acid dissociate almost completely in water. Hydrogen chloride plus water yields hydronium ion plus chloride ion to essentially full conversion under typical conditions. Weak acids donate only a fraction of their protons in water and set up an equilibrium. Acetic acid plus water yields hydronium ion plus acetate ion, but a significant amount of acetic acid remains undissociated. Hydrofluoric acid is a useful cautionary tale. It is a weak acid in terms of dissociation. Yet, it is highly corrosive because fluoride complexes strongly with silicon and penetrates tissues. Chemical effect and acid strength are not the same idea. Many acids can donate more than one proton in steps. These are polyprotic acids, and each step is weaker than the one before. Carbonic acid illustrates the pattern. Carbonic acid plus water yields hydronium ion plus bicarbonate ion. Then bicarbonate ion plus water yields hydronium ion plus carbonate ion. The first deprotonation is easier than the second because removing the second proton leaves charge more concentrated on the remaining base. Phosphoric acid shows 3 steps cleanly. Phosphoric acid plus water yields hydronium ion plus dihydrogen phosphate ion. Dihydrogen phosphate ion plus water yields hydronium ion plus hydrogen phosphate ion. Hydrogen phosphate ion plus water yields hydronium ion plus phosphate ion. Each successive equilibrium lies further to the left, reflecting the decreasing tendency to give up additional protons. Thread these definitions and patterns together, and a practical picture emerges. In water, Arrhenius language helps you predict conductivity and pH. Across solvents and gas phase reactions, Brunstad-Lowry proton transfers keep the logic straight with conjugate pairs. In coordination chemistry and many organic mechanisms, the Lewis view reveals who donates electrons and who accepts them. Amphoteric players switch roles with the environment. Strong acids dissociate nearly completely. Weak acids establish a balance, and polyprotic acids step down their donations in orderly fashion. With these lenses aligned, acid-base behavior becomes less a set of disconnected rules and more a unified story of protons and electron pairs finding their most comfortable homes. pH is a simple way to talk about acidity using a friendly scale. It is defined as the negative logarithm base 10 of the hydronium ion concentration. In words, pH equals negative log base 10 of the hydronium ion concentration. A small hydronium concentration gives a larger pH number, and a large hydronium concentration gives a smaller pH number. Its partner, POH, is defined the same way for hydroxide. POH equals negative log base 10 of the hydroxide ion concentration. Because the scale is logarithmic, each 1 unit change is a 10-fold change in concentration, a neat way to compress huge ranges into numbers that fit on a line. At 25 degrees Celsius, hydronium and hydroxide are tied together by water's autoionization constant. The product of their concentrations is fixed. Hydronium ion concentration multiplied by hydroxide ion concentration equals 1.0 times 10 to the minus 14. to the power of -14. Take negative logs and you get a handy rule. pH plus pOH equals 14.00 at 25 degrees Celsius. Change the temperature and the constant shift a bit, but the logic remains. If you know one, you can find the other. Buffers are the shock absorbers of pH. A buffer solution resists changes in pH when small amounts of acid or base are added. It is built from a weak acid paired with its conjugate base, or a weak base paired with its conjugate acid. The weak acid mops up added hydroxide by donating protons. The conjugate base mops up added hydronium by accepting protons. Because both forms are present in meaningful amounts, the solution has a built-in capacity to neutralize nudges in either direction. Blood, for example, relies on a carbonate-bicarbonate buffer to keep its pH within a narrow, life-friendly range. The arithmetic for buffers is compact and memorable, the Henderson-Hasselbalch equation. In words, pH equals pKa plus log base 10 of the ratio of base to acid. Here, pKa is the negative log base, 10 of the acid's dissociation constant, and base means the concentration of the conjugate base, while acid means the concentration of the weak acid. If base equals acid, the log term is 0, and pH equals pKa. Shifting the ratio by a factor of 10 changes pH by 1 unit. This is why a good buffer keeps the base-to-acid ratio reasonably close to 1, and why choosing an acid with a pKa near the target pH gives the best performance. Colourful dyes called indicators let your eyes track pH, but they do not flip at a single razor-thin point. Each indicator changes colour over a range of pH values, typically spanning about 2 units, centred near the indicator's own pKa. Methyl orange shifts in the acidic region, phenolphthalein shifts in the basic region. Universal indicator blends several dyes to cover a wide spectrum. Pick an indicator whose transition range straddles the pH you expect at the endpoint, and the colour change will be timely and clear. When you titrate, you drip a titrant of known concentration into an analyte of unknown concentration and watch how pH evolves. Plotting pH against the volume added gives a titration curve that reveals key landmarks. In a strong acid-strong base titration, the curve is steep near the equivalence point, and the pH at equivalence is close to 7 at 25 degrees Celsius. In a weak acid-strong base titration, you'll see a gentle flat region before the jump. That is the buffer region, where the weak acid and its conjugate base are both present, and the Henderson-Hasselbalch equation describes the pH neatly. At exactly half neutralization, base equals acid, so pH equals pKa. A convenient way to measure pKa from a curve. After the equivalence point, the excess strong base dominates and the pH rises more gradually. Reverse the roles for a weak base-strong acid titration, and you'll find a buffered region on the acidic side and an equivalence point with pH below 7. Together, these ideas turn pH from a mysterious number into a practical tool. Use the definitions pH equals negative log base 10 of hydronium and pOH equals negative log base 10 of hydroxide. Remember that at 25 degrees Celsius their product is 1.0 times 10 to the power of -14. Build buffers from weak acid-base pairs and tune them with pH equals pKr plus log base, 10 of base over acid. Choose indicators by their transition ranges and read titration curves for equivalence points and buffer plateaus. With that toolkit, you can predict, control, and visualize acidity with confidence. Redox is a duet, not solo. Whenever one species loses electrons, another gains them. Oxidation is loss of electrons. Reduction is gain of electrons. They always occur together because electrons do not vanish into thin air. They leave one place and arrive somewhere else. A classic pair is zinc metal giving electrons to copper 2+ ions. In words, Zinc solid becomes zinc 2 ++ 2 electrons, and copper 2 ++ 2 electrons becomes copper solid. Put them together and electrons flow from zinc to copper, one partner oxidized, the other reduced, the books balance to the last electron. To keep track of who gave up what, chemists assign oxidation numbers, a bookkeeping tool for electron ownership in bonds. Elements in their standard state have oxidation number 0. Oxygen gas, hydrogen gas, sodium metal, all 0. In compounds, oxygen's usually -2. Hydrogen is usually +1 when bonded to nonmetals, and the sum of oxidation numbers matches the overall charge. In iron 3 oxide, each oxygen is -2. 3 of them give -6 total, so the 2 ions must supply +6 in all, making each ion +3. The numbers do not claim that electrons truly move that way in a covalent bond. They simply let you count consistently across reactions. Balancing redox reactions is easiest if you split them into 2 half reactions and let the medium help. In acidic solution, you balance atoms other than oxygen and hydrogen first, then add water to fix oxygen, add hydrogen ion to fix hydrogen, and finally add electrons to balance charge. In basic solution, you balance with water and electrons as before, but you use hydroxide ion instead of hydrogen ion, and you can eliminate any hydrogen ion that appears by adding equal hydroxide to both sides, forming water that you then simplify. Multiply the half reactions so the electrons cancel, add them together, and you have a balanced redox equation with both mass and charge in order. A galvanic cell turns that electron shuffle into useful work. Separate the oxidation and reduction half reactions into 2 compartments, connect them with a wire and a salt bridge, and a spontaneous redox reaction drives electrons through the external circuit. In the classic zinc-copper setup, zinc metal oxidizes at the anode, sending electrons into the wire. Copper 2+ in the other beaker is reduced at the cathode, accepting those electrons to plate out copper metal. The energy that would have been lost as heat in a single mixed beaker becomes electrical energy you can measure, or power something with. The push behind the electron shows up as a cell potential. Under standard conditions, the standard cell potential equals the standard reduction potential of the cathode minus the standard reduction potential of the anode. In words, E standard cell equals E standard cathode minus E standard anode. Because tabulated values are written as reductions, you flip the sign only conceptually for the anode's oxidation, then subtract. A positive E standard cell means the reaction is thermodynamically favourable as written under standard conditions. A negative value means it is not. This tidy subtraction lets you predict which way electrons will naturally flow and how much electrical pressure the cell provides. Inside the cell, charge balance is maintained by ions, not by the electrons in the wire. Electrons leave the anode and travel through the external circuit to the cathode. Meanwhile, ions migrate through the salt bridge. Anions drift toward the anode compartment to neutralize the growing positive charge as metal atoms become cations, and cations drift toward the cathode compartment to replace the positive charge consumed as cations are reduced to metal. Without this quiet ionic traffic, the compartments would quickly charge up and the electron flow would stall. With it, the cell hums along steadily, electrons in the wire, ions in the bridge, and chemistry doing electrical work one electron at a time. The push behind a real electrochemical cell depends on conditions, and the Nernst equation shows exactly how. It says the cell potential at a given temperature equals the standard cell potential minus the gas constant times temperature divided by n times Faraday's constant, multiplied by the natural log of the reaction quotient. In words, E equals E standard minus RT over NF times natural log of Q. As product concentrations rise or reactant concentrations fall, Q grows and the driving voltage drops. Dilute the products or enrich the reactants and the voltage climbs back. Temperature matters too. Warmer conditions change the size of the RT over NF factor and can tilt the balance in cells that move protons or electrons alongside coupled equilibria. The Nernst equation is a chemist's altimeter. It tells you how far above or below standard your cell is flying. Sometimes chemistry will not go on its own, and that is when electricity plays chauffeur. Electrolysis uses an external power source to drive a non-spontaneous reaction. Hook a battery to 2 inert electrodes dipped in brine, and you can split sodium chloride solution into chlorine gas at the anode and hydrogen gas plus sodium hydroxide in the cathode compartment. Run a strong current through molten aluminum oxide with dissolved cryolite, and you coax aluminum metal out at the cathode, while carbon anodes feed oxygen to form carbon dioxide. The Hawley-Rule process that gave modern aluminum to the world. In electroplating, you deposit a thin layer of nickel, copper, or gold on a surface by forcing metal ions to accept electrons and settle as a shiny protective skin. In each case, the power supply pays the energy bill to move electrons in the unfavourable direction. How much substance can you make or move with a given amount of charge? Faraday's laws give the crisp answer. The moles of a species transformed at an electrode equal the total charge passed divided by Faraday's constant times n, where n is the number of electrons per ion in the electrode reaction. In words, moles equal charge divided by F times n. Faraday's constant is about 96,485 coulombs per mole of electrons. Past 9,648.5 coulombs, 1/10 of a Faraday, through a cell that reduces silver 1+ to silver metal, n equals 1, and you will deposit about 1/10 of a mole of electrons worth, which is 1/10 of a mole of silver atoms on the cathode. Double the current or the time and you double the mass plated. It is accounting as exact as a scale. Not all electrochemistry is helpful, sometimes it eats bridges. Corrosion is a spontaneous redox process in which metals oxidize, often with oxygen and water completing the circuit. On iron, tiny galvanic cells form where one spot acts as an anode. Iron becomes iron 2+, and a nearby spot acts as a cathode. Oxygen reduces to hydroxide. The products meet to form iron oxides and hydroxides, rust, and the metal slowly vanishes. Engineers fight back with coatings that block oxygen and moisture, and with sacrificial anodes made of a more reactive metal such as zinc or magnesium. The sacrificial metal oxidizes preferentially, donating electrons to protect the iron or steel structure. Boats, pipelines, and water heaters all live longer with a steady diet of sacrificial anode electrons. Put multiple cells in a package, and you have a battery tailored to a job. Wire cells in series and voltages add. Wire them in parallel and capacity and maximum current add. Modern lithium-ion batteries store and release energy by intercalation. Lithium ions slip in and out of layered or tunneled host materials without breaking the lattice. During discharge, lithium atoms in the anode give up electrons to the circuit and lithium ions migrate through the electrolyte to the cathode, where they insert into sites between metal oxide layers while the electrons arrive through the wire to complete the reduction. During charging, an external power source pulls the process in reverse, extracting lithium from the cathode and tucking it back into the anode. Because no bulk phase change is needed and bonds are mostly preserved, lithium-ion cells combine high energy density with good cycle life, from phones to electric vehicles. Fuel cells take the galvanic idea and run it continuously. Feed a fuel and an oxidizer to opposite sides of a membrane electrode assembly, and the redox reaction generates electricity as long as reactants keep flowing. In a hydrogen fuel cell, hydrogen gas at the anode splits into protons and electrons. The protons travel through the electrolyte while the electrons travel through the external circuit doing work. At the cathode, oxygen gas meets incoming electrons and protons to form liquid water. There is no combustion flame, just electrochemistry, so efficiencies can be high and the only exhaust is water. Other fuel cells sip methanol, natural gas-derived hydrogen, or even ammonia, but the principle is the same. Separate oxidation and reduction, collect the electrons, and keep the reactants coming. From Nernst's compass that guides voltage under real conditions, to the brute force drive of electrolysis, to Faraday's exact conversion between charge and matter, to the everyday battles against corrosion, to the engineered choreography inside lithium-ion cells, and the elegant continuous output of fuel cells. Electrochemistry is where electrons become a tool you can aim, meter, and harness. It is chemistry wired for work. Life runs on electron handshakes. In cellular respiration, the sugar glucose is oxidized. It gives up electrons, while oxygen is reduced. It accepts those electrons and becomes water. The cell does not let that energy spill out all at once. Instead, it passes electrons stepwise through protein complexes in the mitochondria, coupling each tiny downhill electron move to the uphill job of pumping protons. Those protons then flow back through the molecular turbine ATP synthase to make ATP, the cell's spendable energy. It is elegant thrift. Take the high-energy electrons from food, pay some of that energy forward into a proton gradient, and cash it in as chemical currency, with carbon dioxide and water as the calm, low-energy products. Plants and many microbes play the inverse symphony in photosynthesis. Light energy lifts electrons to higher energy states in chlorophyll, and that excited energy is used to reduce carbon dioxide into carbohydrates. In the oxygenic pathway that fills our air, water is split to provide electrons, and oxygen gas is released as a byproduct. The electrons move through an electron transport chain in the chloroplast, again building a proton gradient, again turning the rotor of ATP synthase. But this time the energy came first from sunlight. By storing it in sugars, photosynthesis tucks summer sun into starch and cellulose, saving it for nights, winters, and the rest of the food web. To move electrons with precision, biology enlists redox active metals such as iron and copper. In hemoglobin and cytochromes, iron toggles between iron 2 and iron 3 to carry oxygen or to pass electrons along a chain. In enzymes like superoxide dismutase, copper cycles between copper 1 and copper 2, taming reactive oxygen species that would otherwise damage cells. Iron-sulfur clusters, tiny mineral-like cofactors built right into proteins, hop electrons across nanometer distances with reliable speed. Each metal's preferred redox couple and coordination geometry tunes its working voltage, so proteins can arrange the path like a ladder, each rung just a little lower in energy than the last, making electron flow smooth and directional. Oxidants can be dangerous in the wrong context, and that danger is exactly why we use them to disinfect. Ozone and hypochlorite, the active agent in common bleach, are strong oxidizing agents that react with the double bonds in lipids, the sulfur in proteins, and the nucleic acids in microbes. By stealing electrons, they break essential molecular structures and disrupt metabolism. Used carefully, they purify water, sanitize surfaces, and make hospitals safer. This same reactivity means they must be handled with respect. Too much oxidant or poor ventilation, and you're not just cleaning, you're corroding. In the analytical lab, controlled redox becomes a measuring stick. Redox titrations use a solution of a known oxidizing or reducing agent to determine the concentration of an unknown. Potassium permanganate is a favourite oxidant. Deep purple in solution, it turns colourless or pale pink as it is reduced in acidic conditions, providing its own visual signal with no indicator needed. As you add it to the analyte, the purple fades until the tiniest excess leaves a lasting blush, the endpoint. From the volume of permanganate used and the balanced redox equation, you calculate how much analyte was present. It is chemistry as arithmetic with colour. Beyond the lab glass, natural waters quietly organise themselves into redox layers that shape whole ecosystems. At the oxygen-rich surface of a lake or the fast-flowing stretch of a river, oxidizing conditions prevail. Iron sits as insoluble iron 3 hydroxides, and nutrients like ammonium are converted to nitrate. Deeper down, where oxygen is scarce, microbes switch to alternative electron acceptors, nitrate, then manganese 4, then iron 3, then sulfate. Each step changing which minerals dissolve and which precipitate. In sediments, iron 2 can leach into pore waters. Sulfide produced by sulfate-reducing bacteria combine metals into insoluble sulfides. These redox gradients govern the mobility of arsenic, the availability of phosphorus, the fate of organic carbon, and the vivid banding you see when cores are pulled from the mud. A lake at dawn, a wetland at dusk, an estuary at slack tide, each is a living battery, discharging and recharging as currents, seasons and microbes shuffle electrons between sky, water and stone. From mitochondria sipping electrons one at a time, to leaves stockpiling sunlight as sugar, to copper and iron relaying charges in proteins, to disinfectants knocking out pathogens, to purple permanganate revealing numbers, to rivers and aquifers sorting metals by redox rules. The world is stitched together by oxidation and reduction. Follow the electrons and you can read how life breathes, how water heals itself, and how the planet quietly rewrites its chemistry with every sunrise. Carbon is the great architect of chemistry. Its carbon-carbon bond is strong and directional, and each carbon can make 4 bonds arranged neatly in space. That simple quartet allows carbon atoms to link into straight chains, branched trees, and snug rings, then stack those shapes into ladders, cages, sheets, and frameworks. Add a few other elements and the possibilities explode into millions upon millions of structures. The reliability of the carbon-carbon bond lets a molecule keep its shape long enough to matter, to smell like peppermint, to store energy like fat, to transmit signals like hormones, to encode instructions like DNA. Give carbon 4 bonding hands and it builds a universe of forms. Within that universe, the simplest families are the hydrocarbons. Saturated hydrocarbons, the alkanes, use only single bonds. They are like flexible strings. You can twist and bend them freely and they burn cleanly to carbon dioxide and water. Unsaturated hydrocarbons introduce rigidity and reactivity. Alkenes contain at least one carbon-carbon double bond, which locks parts of the molecule into a plane and creates the potential for easy cis-trans isomerism. Alkynes take it further with a carbon-carbon triple bond, linear and taut like a drawn bow, storing energy in a compact link. With each step, single to double to triple, the bond gets shorter and stronger, and the surrounding geometry shifts from tetrahedral to trigonal planar to linear. A small change in bonding, a big change in behaviour. Some rings get a special passport stamped aromatic aromaticity appears in cyclic planar, conjugated systems that host a specific count of pi electrons, 4n+2, where n is a whole number. Benzene, with 6 pi electrons, n equals 1, is the classic example. Its electrons are delocalized over the ring, making all carbon-carbon bonds equal and conferring unusual stability. That stability shapes reactivity. Aromatic rings tend to substitute rather than add, preserving the magical circle of electrons. Aromaticity is not just a textbook box to tick. It is the reason dyes are colourful. Many medicines are stable in the body, and the scent of cloves or cinnamon lingers. Their molecules carry sturdy, delocalized rings that interact with light and receptors in distinctive ways. Even with the same atoms, connectivity can tell a different tale. Constitutional isomers share a molecular formula, but differ in how those atoms are connected, who is bonded to whom. C4H10 can be a straight chain, butane, or a branched chain, isobutane, and these two have different boiling points, different vapor pressures, and even different uses. Scale that up and the diversity explodes. The number of constitutional isomers for long-chain hydrocarbons grows into the many millions as the carbon count rises. This is why one formula can hide a crowd of candidates, and why techniques like NMR and mass spectrometry are essential to tell them apart. Functional groups are the recurring characters that define how molecules behave. An alcohol group, OH, brings hydrogen bonding and makes a compound more soluble in water. An amine, NH2, NH or N, turns a molecule basic and eager to bind acids or metals. Carbonyl groups, aldehydes and ketones, polarize bonds and invite nucleophiles to attack the electrophilic carbon. Carboxylic acids donate protons and form strong hydrogen bonds. Esters smell fruity and are more reluctant to react with bases. Amides are astonishingly tough due to resonance, which is why peptide bonds in proteins hold firm. Spot the functional group and you can often predict the plot. How the molecule will react, what it will dissolve in, and even how it might taste or smell. Bring in heteroatoms, elements other than carbon and hydrogen, and you change the electrical landscape. Oxygen, nitrogen, sulfur and halogens carry lone pairs and distinct electronegativities, which create polar bonds. Polarity shifts electron density, making some sites electron-rich nucleophilic and others electron-poor electrophilic. An oxygen atom can both donate a lone pair to hydrogen bond and withdraw electron density from its neighbouring carbon, increasing acidity. A halogen can stabilize a nearby positive charge by induction, yet leave a carbon susceptible to substitution or elimination. Nitrogen's lone pair can grab a proton, bind a metal, or attack a carbonyl. With heteroatoms, a carbon skeleton becomes a nuanced landscape of hills and valleys for electrons, and that terrain guides every reaction the molecule will attempt. Put all of this together and organic structure becomes a readable language. Carbon supplies a sturdy grammar of chains and rings. Saturation and unsaturation set the rhythm between flexibility and rigidity. Aromatic rings add a chorus of delocalized stability. Constitutional isomers change meaning by rearranging the same letters. Functional groups deliver recognizable verbs: donate, accept, attack, stabilize. And heteroatoms adjust tone and emphasis with polarity and lone pairs. Once you learn to hear that language, a line drawing on a page turns into a living script of reactivity, properties, scent, color, and purpose. Organic reactions often read like a conversation between opposites. Nucleophiles are electron pair donors, think nucleo for nucleus loving, attracted to positive or electron poor spots. Electrophiles are electron pair acceptors. They welcome extra electron density. Put them in the same room and chemistry happens. The nucleophile's lone pair reaches toward an electrophilic carbon, a bond forms, and some other group may leave to make space. Water, alcohols, amines, enolates, and halide ions often play the nucleophile. Carbonyl carbons, protonated alkenes, and alkyl halides often play the electrophile. Learn to spot where electrons are abundant and where they are hungry, and you can predict the first move. Two big families of reactions reshape double bonds. In an addition reaction, atoms add across a carbon-carbon double bond, converting it into single bonds. Hydrogen halide addition is a classic. The pi bond grabs a proton, generating a carbocation, and the halide then attaches to that positively charged carbon. Hydroboration oxidation is another, arriving at alcohols with distinctive anti-Markovnikov placement. The opposite move is elimination, where a base plucks a proton while a leaving group departs, and a double bond springs into place between the two carbons. Dehydrohalogenation, removing hydrogen and halide, is the textbook example. Conditions decide the winner. Heat and strong, bulky bases tilt toward elimination. Gentle nucleophiles and cooler temperatures lean toward addition or substitution. Substitution reactions are the switchboard operators of saturated carbons. One group exits, another takes its place. Two archetypes set the stage. SN2 is a single, concerted step. The nucleophile attacks from the backside while the leaving group departs, giving inversion of configuration at a chiral center. It prefers primary carbons, strong nucleophiles, and polar aprotic solvents like acetone or dimethyl sulfoxide. SN1 is a two-step dance. The leaving group departs first to form a carbocation, then the nucleophile attacks. It thrives on tertiary carbons where the carbocation is stabilized, and it often leads to racemization, because the flat carbocation can be attacked from either side. Choosing reagents and conditions is like tuning a radio between these two channels. When organic chemists talk about oxidation and reduction, they are not always counting electrons directly. They watch bonds. Oxidation usually means increasing the number of bonds to oxygen or other electronegative atoms, or decreasing the number of bonds to hydrogen. Reduction means the reverse: more bonds to hydrogen or fewer to oxygen. Alcohol to aldehyde to carboxylic acid is a path of oxidation. Ketone to alcohol is reduction. Hydrogenation across a double bond is reduction. Ozonolysis that cleaves a double bond into carbonyls is oxidation. These definitions track with electron flow, but they are far quicker to spot on a line drawing. Carbocations sit at the crossroads of many mechanisms. They are electron-poor intermediates with only 6 electrons around carbon, and they crave stabilization. Alkyl groups help by hyperconjugation. Overlapping adjacent CH bonds can donate a little electron density, so a tertiary carbocation is more stable than a secondary, which is more stable than a primary. Resonance is an even stronger ally. If the positive charge can be delocalized into a benzene ring or shared with an adjacent pi bond, the carbocation calms down. These preferences explain rearrangements like hydride or methyl shifts. The intermediate will shuffle groups to reach a more stable carbocation before the next step occurs. Spotting potential rearrangements helps you predict unexpected products that appear out of nowhere. Not all pathways use paired electrons. Radical reactions proceed one electron at a time, generating intermediates with a single unpaired electron. Light or peroxides often start the show by homolytic bond cleavage. Each atom takes one electron. Once a radical forms, it can add to a double bond, abstract a hydrogen, or trigger chain processes with 3 phases: initiation to create radicals, propagation steps that repeat and build product, while regenerating a radical, and termination when 2 radicals meet and neutralize each other. Alkane halogenation under bright light is a classic. Chlorine radicals abstract a hydrogen to make hydrogen chloride and an alkyl radical. The alkyl radical then meets chlorine gas to give an alkyl chloride and another chlorine radical. Because radicals are less choosy about orientation than ionic mechanisms, they often lead to different selectivities. Bromination at tertiary positions, for example, thanks to more stable radical intermediates. Thread these ideas together and reactivity turns into a readable map. Look for electron-rich nucleophiles aiming at electron-poor electrophiles. Expect additions to decorate double bonds and eliminations to carve them out. Choose between substitution routes by asking whether the carbon can host a carbocation or whether a concerted backside strike is more likely. Track oxidation and reduction by counting bonds to oxygen and hydrogen. Stabilize or anticipate carbocations with hyperconjugation and resonance, and beware of rearrangements. And when light or peroxides are present, consider radical pathways with their single electron logic. With this toolkit, the arrows you draw on the page start to feel like reliable road signs through the landscape of organic reactions. Alcohols are crossroads in organic chemistry, able to head up by oxidation or down by reduction. A primary alcohol can be oxidized to an aldehyde, and with stronger or continued oxidation, that aldehyde can be taken further to a carboxylic acid. A secondary alcohol oxidizes to a ketone, which generally resists further oxidation under ordinary conditions because there is no hydrogen on the carbonyl carbon to remove. The story is about bonds. Increasing the number of carbon-oxygen bonds and decreasing the number of carbon-hydrogen bonds counts as oxidation. In synthesis, chemists choose reagents to stop at the aldehyde, a gentle oxidant and careful conditions, or to push onto the acid with a stronger hand. In living systems, enzymes perform similarly precise oxidations, turning ethanol into acetaldehyde and then into acetic acid with exquisite control. Carboxylic acids have their own signature transformation, esterification. When a carboxylic acid meets an alcohol in the presence of an acid catalyst, they combine to form an ester and water. In words, carboxylic acid plus alcohol yields ester plus water. The mechanism is a tidy sequence. Protonate the carbonyl to make it more electrophilic, let the alcohol's oxygen attack, shuffle protons, and then lose water to reform the carbonyl as an ester. The reaction is reversible, so practical work often nudges the balance by removing water as it forms, or by using an excess of one partner. The result is a new, pleasantly scented bond. Many fruit and flower aromas are esters, and chemists tune flavours and fragrances by swapping alcohols and acids like notes on a scale. Nitrogen changes the tone of a molecule. Amines, with a nitrogen that carries a lone pair, are both basic and nucleophilic. They readily accept a proton to become ammonium ions, and they readily donate that lone pair to attack electrophilic carbons, forming new carbon-nitrogen bonds. This is the backbone of many pharmaceuticals and dyes. Amides, despite having nitrogen, behave very differently. In an amide, the nitrogen's lone pair delocalizes into the adjacent carbonyl, sharing electron density by resonance. That sharing makes the carbonyl stronger and the nitrogen less basic, far less eager to grab a proton or to attack. It also makes the CN bond in an amide tougher, with partial double bond character. That is why peptide bonds in proteins are so robust. Resonance tethers the structure, resisting hydrolysis unless enzymes or strong conditions intervene. Carbonyl compounds, aldehydes and ketones, are classic electrophiles that invite nucleophilic addition. The polarized carbon-oxygen double bond places a substantial partial positive charge on the carbonyl carbon. A nucleophile attacks that carbon. The pi bond to oxygen collapses upward to form an alkoxide, and after protonation, you have added across the double bond. Cyanide adds to give cyanohydrins. Hydride donors such as sodium borohydride reduce the carbonyl to an alcohol. Organometallic reagents such as Grignards add carbon-carbon bonds, building bigger frameworks in a single, satisfying step. Aldehydes are typically more reactive than ketones because they are less hindered, and their carbonyl carbons are a little more positively polarized. Ethers are the quiet, dependable solvents of organic chemistry, and their reactivity reflects that calm. The oxygen in an ether bridges two carbon chains with single bonds, and without a reactive carbonyl or a strongly polarized bond, ethers are generally reluctant to participate in many reactions. They resist bases and many nucleophiles, making them good media for sensitive reagents. However, strong acids can coax them to cleave. In the presence of concentrated hydrohalic acids such as hydrogen iodide or hydrogen bromide, an ether can be protonated at oxygen, turning a weak cleaving group into a better one. Then a nucleophilic halide attacks, splitting the ether into an alcohol and an alkyl halide, or into two alkyl halides under harsher conditions. It is a reminder that unreactive often means unreactive until pushed. Alkyl halides are the versatile switchboards of organic reactions because the carbon-halogen bond is polarized, and the halide is a decent leaving group. In substitution, a nucleophile steps in as the halide steps out. If the carbon is primary and the nucleophile is strong, a one-step SN2 mechanism often wins, with backside attack and inversion at a stereo center. If the carbon is tertiary and the solvent is polar and protic, the bond may ionize first to give a carbocation, inviting a two-step SN1 pathway where the nucleophile arrives later, often with loss of stereochemical information. Under basic warmer conditions, especially with bulky bases, elimination competes. The base removes a beta hydrogen, the halide leaves, and a double bond forms. Which path dominates depends on the substrate, the strength and bulk of the nucleophile or base, the solvent, and the temperature. With a good leaving group at a flexible carbon, you have a reaction fork, substitution to swap partners, or elimination to carve a new pi bond. Taken together, these functional group themes turn a dense chart into a storybook of reactivity. Alcohols climb the oxidation ladder to aldehydes, ketones, and acids. Carboxylic acids and alcohols clasp hands to become esters, shedding water as they bond. Amines bring basicity and nuclear felicity, while amides trade that away for resonant stiffened stability. Carbonyls invite additions that build new bonds with surgical precision. Ethers mind their own business until strong acid insists on a breakup. Halides stand ready at the crossroads, channeling traffic towards substitution or elimination. Learn each group's habits, and organic synthesis becomes less a maze and more a well-marked path from simple building blocks to complex, purposeful molecules. Hold a molecule up to a mirror and chemistry can split into two different worlds. If a carbon atom is bonded to 4 different substituents, it becomes a chiral center, and the molecule can exist as 2 non-superimposable mirror images called enantiomers. Like left and right hands, they match in outline but cannot be perfectly overlaid. The atoms are the same and the bonds are the same, yet the 3-dimensional arrangement is different, and that subtle twist can change smell, taste, and biological activity in striking ways. Mix those mirror images in exactly equal amounts and you have a racemic mixture. Each enantiomer rotates plane polarized light in equal magnitude but opposite directions, so together they cancel, and the mixture is optically inactive overall. It is like 2 equally strong violinists playing the same note a perfect half cycle out of phase. The sound vanishes to silence. Chemically, however, that silence can still be busy. Racemates may crystallize differently from their pure enantiomers, and chiral environments, like enzymes, will often separate or react with one hand faster than the other. Not all stereochemical siblings are mirror images. Diastereomers are stereoisomers that are not mirror images, and unlike enantiomers, they generally have different melting points, boiling points, densities, and even solubilities. 2 sugars with the same formula can be diastereomers and taste different. 2 drug candidates can be diastereomers, and one may crystallize neatly, while the other stubbornly oils out. Because their physical properties differ, diastereomers are often easier to separate than enantiomers, a practical gift to synthetic chemists. Double bonds bring their own brand of geometry, labelled with E-Z notation. To assign it, give each carbon of the double bond a priority for its 2 substituents, using the Kahn-Ingold Prelog rules, Higher atomic number means higher priority. If tied, look outward along the chain. If the higher priority groups are on the same side of the double bond, the alkene is Z'd from the German zusammen together. If they are on opposite sides, it is E from entgegen, opposite. This system works even when cis and trans would be ambiguous, and it maps directly onto properties like boiling point and reactivity that depend on shape. At a single chiral center, absolute configuration is captured by R-S notation. Rank the 4 substituents by the same priority rules, orient the molecule so the lowest priority group points away from you, and trace a path from highest to second to third. If the path turns clockwise, the configuration is R, from the Latin rectus, right? If it turns counterclockwise, it is S, from sinister, left. R and S do not tell you which way plane polarized light is rotated. That must be measured, but they do give an unambiguous structural label that any chemist anywhere can reproduce from a drawing. Living systems are exquisitely picky about handedness. Enzymes, receptors, and transporters are themselves chiral, so they often recognize one enantiomer far better than the other. One enantiomer of limonene smells like oranges. Its mirror image smells like pine. One enantiomer of a medicine may bind tightly and help. The other may be weaker, inactive, or even cause side effects. That is why modern drug synthesis and analysis are obsessed with stereocontrol and chiral purity. In biology, a mirror image can be a different story entirely. Polymers are long stories told in repeating words, and the way those words link changes everything. In addition, polymerization, monomers with double bonds open those pi bonds like doors and join hands end to end. No small molecules leave. The chain simply grows as each new double bond adds to the reactive end. Vinyl chloride turns into polyvinyl chloride. Ethene becomes polyethylene. Styrene becomes polystyrene. Often a radical, cation or anion starts the chain, and once it is moving, the process cascades. Initiation creates the first reactive site, propagation adds monomer after monomer in a rapid march, and termination finally caps the chain. The key point is the bookkeeping. The atoms you start with end up in the backbone. Condensation, polymerization writes a different kind of sentence, punctuated by the release of tiny byproducts. Two complementary functional groups react to form a bond while eliminating a small molecule such as water or methanol. Diacids with diols form polyesters. Diamines with diacids form polyamides like nylon. Bisphenol A with epichlorohydrin yields epoxy networks. Each new link comes with a tiny farewell, a drop of water here, a whiff of methanol there, and the chain lengthens as those small molecules depart. Because functionality matters, monomer design is like engineering a zipper. You need matching teeth on both sides to get a strong, even closure. Heat treats polymers according to how they are built. Thermoplastics are like wax. They soften when warmed and can be reshaped because their chains are not permanently tied together. Melt and mould, cool and harden, repeat as needed. Thermosets are different. Once cured, they form cross-linked networks where chains are tied together at many points. That network cannot flow when heated. Instead, it chars or decomposes. Epoxies, vulcanized rubber, and many resins are thermosets, chosen when rigidity, heat resistance, or chemical resilience matters more than recyclability. A polymer's personality depends on chain length, branching, and crystallinity. Longer chains tangle more, raising viscosity and strength. Branching changes how neatly chains can pack. High-density polyethylene has very little branching and packs tightly into crystalline regions, making it tough and stiff, while low-density polyethylene has many branches that frustrate packing, yielding a softer, more flexible material. Crystallinity creates ordered lamellae, that raise melting points and improve barrier properties. Amorphous sections lend clarity and impact resistance. Even the glass transition temperature, the point where an amorphous polymer shifts from glassy and brittle to rubbery and flexible, is tuned by how tightly chains interact and how freely they can wiggle. Mixing monomers is a powerful way to tune behavior, and copolymers are the result. Random copolymers sprinkle two monomer types along the chain, smoothing properties between the parents. Block copolymers stitch long runs of one monomer to long runs of another, and those blocks can self-assemble into nanoscale domains that grant rubbery toughness and clear phase-separated morphologies. Think styrene butadiene styrene shoe soles, with hard and soft layers interleaved. Graph copolymers hang side chains of one polymer on the backbone of another, creating emulsifiers or impact-modified plastics like ABS, where styrene acrylonitrile backbones carry rubbery butadiene grafts for crack resistance. By changing composition and sequence, engineers dial in flexibility, transparency, gas barrier performance, and processability. Not every plastic is here to stay. Biodegradable polymers are designed to come apart under the right conditions, breaking their chains by hydrolysis or with help from enzymes. Polylactic acid hydrolyzes its ester links and composts under industrial conditions. Polycaprolactone and polyglycolide do the same more slowly, which is useful in medical sutures and drug delivery devices that should vanish after their job is done. Polyhydroxyalkanoate is brewed by microbes and can be digested by microbes again, closing a biological loop. Biodegradable does not mean disappears overnight. Temperature, moisture, microbes, and oxygen all matter. But with the correct environment, these materials return to simpler molecules rather than lingering for decades. From addition chains that keep every atom, to condensation steps that leave tiny footprints. From meltable thermoplastics to permanently cross-link thermosets. From backbone length and branching that set strength and flexibility, to copolymer architectures that blend virtues. And finally to polymers that gracefully step off the stage when their performance is over. Macromolecules are a chemistry of design, where small structural choices ripple into the textures, strengths and lifetimes of the things we touch every day. Proteins are long, elegant chains built from a standard toolkit of 20 amino acids. Each amino acid has an amino group and a carboxyl group, and when two meet, they link by forming a peptide bond, a condensation reaction where the carboxyl of one and the amino of the next combine and release water. Stack that reaction thousands of times and you have a polypeptide, a backbone of repeating NCC units with side chains, R groups, jutting out like charms on a bracelet. Those side chains, acidic, basic, polar, non-polar, bulky, or tiny, are the characters that give each protein its personality. The primary structure of a protein is the exact order of those amino acids, letter by letter, like a sentence written in a 20-letter alphabet. From that one-dimensional script springs higher-order structure. The chain folds into local motifs, alpha helices and beta sheets, then packs into a three-dimensional shape that places catalytic residues, binding pockets, and flexible hinges exactly where they're needed. Finally, multiple folded chains may assemble into a larger complex. Sequence begets shape. Shape begets function. Change a single letter in the primary structure, and you can change the meaning of the entire sentence. What holds a folded protein together is a tapestry of small forces working in chorus. Hydrogen bonds stitch alpha helices and beta sheets into place, lining up backbone carbonyls and NH groups with zipper-like regularity. Hydrophobic side chains flee water and huddle together in the interior, driving the overall collapse of the chain. The hydrophobic effect is the backstage crew that dims the house lights and gets the actors on stage. Ionic interactions, salt bridges, bring oppositely charged side chains into snug pairs, adding strength and tuning stability with pH. Disulfide bonds, covalent links between cysteine residues, act as molecular safety pins, locking distant parts of a protein together and hardening extracellular proteins against the rough and tumble outside the cell. Enzymes are proteins, and sometimes RNAs, that make chemistry fast by making the hill smaller. They lower the activation energy of a reaction, increasing the rate, but they do not change the overall equilibrium. Reactants and products still balance as thermodynamics dictates. You can think of an enzyme as a trail crew carving switchbacks up a steep mountain. The summit is the same, but the path is easier and faster to climb. That is why tiny amounts of enzyme can process vast amounts of substrate in short order, again and again. The magic happens in the active site, a pocket or groove where the substrate binds with high specificity. Specificity is not a single handshake, it is a constellation of weak interactions, hydrogen bonds, van der Waals contacts, hydrophobic packing, and precisely placed charges. Some enzymes use induced fit, flexing subtly when the substrate arrives, to align catalytic residues exactly and to stabilize the transition state. Others pre-organize a charged environment so that the toughest step in the reaction is prepaid by complementary electrostatics. Either way, the active site is a carefully arranged microenvironment, more like a custom toolkit than a simple slot. Despite their robustness, proteins are sensitive to their surroundings, and denaturation shows just how much their function depends on shape. Heat, extreme pH, high salt, organic solvents, or heavy metals can disrupt the non-covalent interactions that hold the folded structure together. The protein unravels, losing secondary, tertiary, and quaternary structure, and function vanishes. Crucially, the peptide bonds of the backbone usually remain intact during denaturation. The chain is still there, but the three-dimensional architecture is gone. That is the difference between an egg's clear protein turning opaque in a frying pan, denaturation, and chopping the protein into amino acids, hydrolysis. In the right conditions, some proteins can refold and regain activity. Others need chaperone proteins to guide the process. Still, others are past the point of no return. Put these pieces together and proteins become less mysterious and more inevitable. A linear sequence written by genes folds by local rules into stable motifs, packs by hydrophobic collapse and precise side chain interactions into a functional machine, binds substrates in an active site tailored by evolution, accelerates reactions by easing the hardest step, and unravels when the environmental threads that hold it together are pulled. From silk strength to hemoglobin's oxygen shuttle to enzymes that stitch and snip DNA, the same principles of bonding, folding, and specificity echo across biology's molecular stage. Carbohydrates are nature's quick change artists, switching from sweet, simple sugars to sturdy structural beams with just a change in linkage. Glucose can polymerize into starch for energy storage in plants, using alpha-1,4 links with occasional alpha-1,6 branches in amylopectin that our enzymes can snip for fuel. Arrange the very same glucose in beta-1,4 links and you get cellulose, long straight chains that hydrogen bond into tough fibers, perfect for plant cell walls and terrible for our digestive enzymes. Animals echo starch's logic with glycogen, a highly branched glucose store ready for rapid release. Same monomer, different joinery, wildly different jobs. Lipids assemble membranes by using their split personalities. Each phospholipid has a hydrophilic head that loves water and a pair of hydrophobic tails that avoid it. In water, they spontaneously form bilayers, heads out, tails in, a self-sealing sheet that becomes the cell membrane. Proteins float and drift within this fluid mosaic, carrying signals, pumping ions and ferrying nutrients. Cholesterol slips between tails to keep the membrane from getting too floppy when it is warm and too brittle when it's cold. Under other conditions, lipids can roll into micelles or curve into vesicles, little bubbles that cells use to ship cargo or capture meals. Nucleic acids are life's libraries. DNA stores genetic information in two antiparallel strands coiled into a right-handed double helix. The code is written with 4 bases that pair with exquisite specificity. Adenine pairs with thymine through 2 hydrogen bonds, and cytosine pairs with guanine through 3. Because each strand is a template for its partner, the molecule can be copied with high fidelity, unzip, match the bases, and rewind. RNA reads from this library and acts. Messenger RNA carries instructions. Transfer RNA delivers amino acids. Ribosomal RNA helps build proteins. And many small RNAs fine-tune expression like editors with sharp pencils. A TP is the cell's rechargeable coin, paying for uphill chemistry. Its high-energy phosphanhydride bonds are not spring-stuffed with magic. The hydrolysis simply shifts the balance to more stable, better solvated products. In words, adenosine triphosphate plus water yields adenosine diphosphate plus inorganic phosphate and a proton, releasing usable free energy under cellular conditions. Enzymes couple this to hard tasks, shaping proteins, pumping ions, building polymers, often by forming a brief phosphorylated intermediate. Magnesium ions steady the triphosphate's negative charges, and kinases act as cashiers, moving the phosphate group exactly where it is needed. Enzymes rarely work alone. Many carry small helpers that do the tricky electron or group transfers. Metal-ion cofactors like zinc 2 plus and iron 2 plus polarize bonds or shuttle electrons. Organic coenzymes, often derived from vitamins, do precision courier work. NAD plus and FAD carry hydride or hydrogen atom equivalents in redox reactions. Coenzyme A delivers activated 2-carbon units as thioesters. Pyridoxal phosphate moves amino groups in transamination. Biotin carries carbon dioxide in carboxylations. By swapping these portable parts, a single protein scaffold can handle a wide repertoire of chemistry. Metabolism is choreography, not chaos. Pathways are sequences of enzyme-catalyzed steps that pass intermediates hand to hand, with regulation built in so supply meets demand. Feedback inhibition is a favourite trick. Make enough of the end product and it circles back to slow the first committed step, preventing waste. Allosteric enzymes read the room. Activators or inhibitors bind at regulatory sites and shift the protein shape to speed or slow the flow. Catabolic routes harvest energy by breaking molecules down. Anabolic routes spend that energy to build. Compartmentalization adds another layer. Fatty acid oxidation in mitochondria, fatty acid synthesis in the cytosol. Same actors, different stages, directions never crossed. Alloys are the chef's specials of the metal world. Take a base metal, blend in carefully chosen partners, and you can tune flavor and texture. In engineering terms, strength, toughness, conductivity, and corrosion resistance. Steel is iron seasoned with carbon and often chromium, nickel or molybdenum. Brass is copper mixed with zinc for a golden sheen and easy machinability. Bronze brings copper together with tin for wear resistance. By altering composition and processing, the same family of atoms can become a spring, a scalpel or a skyscraper. Heat treatment is the artistry that follows the recipe. Heat a steel to austenite, quench it fast, and you trap a hard, supersaturated phase called martensite. Temper it, reheat gently, and you trade a bit of hardness for crucial toughness. Annealing softens and relieves internal stresses. Normalizing refines grain size for uniform properties. All of these processes rearrange the microstructure. the sizes and shapes of grains and the phases present. And that invisible landscape determines how the metal bends, dents or cracks when real forces arrive. Stainless steels wear self-healing armour. With enough chromium, typically at least about 12%, the surface oxidizes to a thin, tightly adherent chromium oxide layer that shuts down further corrosion. Scratch it, and in the presence of oxygen, the film reforms on its own. Add nickel for austenitic grades that are easy to form and weld. Add molybdenum to boost pitting resistance in chlorides. The bulk metal provides strength. The nanometers thin passive film provides durability, a partnership that keeps cutlery bright and chemical plants safe. Some alloys remember their youth. Shape memory alloys, the celebrity's nickel titanium, often called nitinol, undergo a reversible, solid-state phase change between martensite and austenite. Deform them in the low-temperature martensitic state, and the distortion twirls through the crystal like a reversible origami fold. Warm them past a transition temperature, and the lattice snaps back to the austenitic form, carrying the macroscopic shape with it. That heat-to-reset trick powers self-expanding stents, actuators, and eyeglass frames that shrug off bends. In the quiet below a critical temperature, certain materials lose all electrical resistance. They become superconductors. Push a current and it flows without dissipation. Bring a magnet close, and the Meissner effect expels the magnetic field, letting the superconductor levitate a magnet like a magic trick with Maxwell's blessings. Traditional low-temperature superconductors need cryogenic baths. Newer high-temperature ceramics operate in liquid nitrogen ranges, still chilly but far more practical. The promise is cables with zero loss, ultra-sensitive magnets for imaging and accelerators, and perhaps one day more accessible power technologies. A tiny atom in a tight spot can make a big difference. Interstitial strengthening occurs when small atoms, carbon, nitrogen, or hydrogen, squeeze into the gaps of a metal lattice, as carbon does in iron. Those interstitials distort the crystal and snag dislocations, the line defects that enable metals to deform. With dislocations pinned, more stress is required to make the lattice slip, so hardness and yield strength rise. This is the essence of steel. A little carbon threaded between iron atoms turns a soft, easily dented metal into a workhorse that holds an edge, bears a load, and builds a city. Ceramics are the stoics of materials, hard, heat-resistant and unflappable under compression, yet prone to sudden failure when stretched or struck. Their atoms are locked together by strong ionic and covalent bonds. Think of aluminum oxide, silicon carbide or zirconium dioxide, which give them high melting points and superb wear resistance. But those same bonds restrict dislocation motion, the microscopic slipping that lets metals bend so cracks in ceramics have little way to blunt or heal. Flaws matter. A tiny surface scratch can focus stress and launch a fracture. Engineers counter this with clever microstructures, adding zirconia to transformation-toughen alumina or designing compressive surface layers. But the fundamental trade-off remains: great stiffness and heat tolerance, bought at the price of brittleness. Glass is a solid that never quite learned the crystal's choreography. It is amorphous. Atoms are arranged like a frozen liquid, without long-range order. Pure silica glass melts at punishing temperatures, so modifiers are added to tune behavior. Sodium oxide lowers the melting point. Calcium oxide restores chemical durability. Together they make everyday soda-lime glass for windows and bottles. Add boron oxide and you get borosilicate glass, which resists thermal shock in labware and cookware. Titania, alumina, and rare earth oxides tweak refractive index and dispersion for optics and fiber communications. By adjusting the network formers and modifiers, glassmakers dial transparency, hardness, thermal expansion, and even how a glass breaks. Semiconductors sit between insulators and metals, and a sprinkle of the right impurity gives them purpose. Doping with donor atoms like phosphorus in silicon creates N-type material with extra electrons ready to conduct. Doping with acceptor atoms, like boron in silicon, creates P-type material with mobile holes, missing electrons that move as positive charges. Join N-type and P-type, and you form a PN junction, the one-way gate at the heart of diodes, transistors, and solar cells. Bias the junction and carrier's flow. Reverse it, and the current nearly stops. With nothing more than a few parts per million of dopants, conductivity can shift by many orders of magnitude. The subtlety that underpins modern electronics. Light-emitting diodes turn electricity straight into light by letting electrons and holes reunite in a semiconductor. When an electron from the conduction band falls into a hole in the valence band, it can release the energy difference as a photon. The colour is set by the band gap. Wider gaps give bluer light, narrower gaps give redder light. Efficient LEDs engineer PN junctions, confining layers, and reflective structures so that most recombinations produce photons and most photons escape. The result is a cool-running, long-lived light source that wastes little energy as heat. Indicator dots, phone screens, street lamps, and plant grow panels all sing from this same quantum chorus. Perovskites are a family of materials with a shared blueprint, the Abex 3 structure, but a dazzling range of personalities. Swap the A-site cation, large, the B-site cation, smaller, or the X-site anion, often oxygen in oxides or halides in solar absorbers, and you tune band gaps, dielectric constants, and magnetic or ferroelectric behavior. Calcium titanate is the namesake. Barium titanate is ferroelectric. Halide perovskites, with lead or tin, absorb sunlight strongly and can be tuned from deep red to sky blue by adjusting the halide mix. That structural flexibility lets researchers dial in electronic and optical properties for sensors, photovoltaics, lasers, and light emitters, a single lattice hosting many technologies. Some plastics behave like wires in disguise. Conducting polymers carry charge along conjugated pi systems, chains of alternating single and double bonds where electrons are delocalized. Polyaniline, polypyrrole, and polythiophene derivatives, like PEDOT:PSS, can be doped to create mobile charge carriers called polarons and bipolarons, turning a dull organic film into a flexible, transparent electrode or a soft biointerface, because they can be printed as inks, stretched, or interfaced with living tissue, conducting polymers, bridge electronics and biology, making bendable circuits, smart textiles, and electrodes that can talk to cells in their own gentle, watery language. High above our heads, a thin shield of ozone soaks up the sun's most harmful ultraviolet rays. Ozone is just oxygen in a different arrangement, 3 atoms instead of 2, but that extra atom makes it uniquely good at absorbing high-energy light before it reaches skin, eyes, and DNA. For decades, chlorofluorocarbons drifted upward from sprays and coolants, and under sunlight split to release chlorine radicals. Those radicals enter catalytic cycles where one chlorine atom can destroy many ozone molecules before being parked temporarily as reservoir species, only to be reawakened by sunlight and keep going. The result was the infamous springtime hole over Antarctica, not a literal hole, but a dramatic thinning. International agreements phasing out these chemicals have helped the layer recover, a rare win where chemistry diagnosed a planetary problem, and chemistry policy helped solve it. Hazy city afternoons have their own chemistry lab in the sky. Photochemical smog forms when nitrogen oxides from engines and power plants meet volatile organic compounds from fuels, solvents, and even trees. Then sunlight flips the switch. A cascade of reactions produces ozone at ground level, great up high, irritating down low, along with a medley of oxidants and secondary organic aerosols. Temperature inversions trap the brew, and the familiar brownish haze builds. Because sunlight drives the chemistry, smog tends to peak on calm, warm days, and the recipe can be tuned by local emissions. Cut nitrogen oxides or volatile organics too unevenly, and you may not get the cleanup you expect. Smart air quality plans balance both sides of the equation. When rain falls through air laced with sulfur dioxide and nitrogen oxides, the droplets become tiny acid factories. In the atmosphere, sulfur dioxide oxidizes to sulfuric acid, and nitrogen oxides become nitric acid. Clouds and fog efficiently dissolve these acids and deliver them to the ground as acid rain. The consequences ripple outward. Lakes lose buffering capacity and become too acidic for fish eggs. Soils leach essential nutrients like calcium. Metals corrode faster. Limestone carvings soften. Flue gas desulfurization, low sulfur fuels and catalytic converters have slashed many emissions, proving that targeted chemical controls can protect ecosystems without turning off the lights. Some gases act like a comforter around the planet. Greenhouse gases such as carbon dioxide, methane, nitrous oxide, and water vapor absorb infrared radiation that Earth emits after it warms in sunlight, then re-emit that energy in all directions, including back down. This slows the escape of heat, nudging surface temperatures upward. Different gases trap heat with different strengths and lifetimes. Methane packs a stronger short-term punch, but persists for a shorter time than carbon dioxide. Carbon dioxide is gentler per molecule, but lingers, accumulating with every ton emitted. Understanding their spectra and life cycles is the chemistry behind climate models, and the reason reducing long-lived emissions is central to stabilizing temperatures. Not all air pollution is invisible. Particulate matter, tiny solid and liquid particles suspended in air, affects health and climate in ways that depend on size and composition. PM10 particles 10 micrometers and smaller can irritate the upper airways. PM 2.5, 2.5 micrometers, and smaller penetrates deep into lungs and can enter the bloodstream. Soot absorbs sunlight and warms. Sulfate and nitrate aerosols scatter light and cool. Organic aerosols can do both, depending on their mix. Particles also carry metals and organics that trigger inflammation. Chemistry determines how these particles form, direct emissions versus secondary formation, how long they linger, and how best to remove their sources. Above cities and forests alike, atmospheric chemistry quietly runs the nitrogen-sulfur cycles that set the stage for life. Nitrogen oxides formed in lightning and engines can become nitric acid and ultimately nitrates that fertilize soils. Helpful in moderation, harmful in excess when they overfeed waterways. Sulfur from volcanoes and combustion converts to sulfate aerosols that seed clouds and alter Earth's reflectivity. Microbes close loops at the surface, reducing nitrates back to nitrogen gas, or oxidizing reduced sulfur to sulfate, while winds and sunlight keep reagents moving. The sky is not empty. It is a dynamic reactor that shuttles atoms among reservoirs, deciding whether nutrients nourish, metals rust, skies clear, or haze forms. When tap water leaves spots on glassware and soap refuses to lather, the culprit is often hardness, mainly calcium 2+, and magnesium 2+ ions dissolved from limestone and dolomite. These ions grab onto soap to form insoluble scum and compete in detergents with the cleaning you actually want. One elegant fix is ion exchange. In a softener, a resin loaded with sodium plus, or sometimes potassium plus, trades places with incoming calcium 2+ and magnesium 2+, capturing the hardness ions and releasing harmless sodium plus into the water. When the resin fills up, a brine rinse resets it, sending the captured calcium and magnesium down the drain and restoring the resin's appetite. Give a lake too much fertilizer and it throws a green party with an ugly hangover. Eutrophication happens when nutrient runoff, mostly nitrates and phosphates from agriculture, lawns and wastewater, fuels explosive algal and cyanobacterial blooms. At first, photosynthesis may spike oxygen in daylight, but when the bloom dies, microbes feast on the sinking biomass and consume dissolved oxygen in the process. Oxygen drops, fish suffocate, and bottom-dwelling creatures flee or perish. The water turns murky, food webs skew, and toxins from some species can make matters worse. The chemistry cure is prevention. Cut nutrient inputs, restore wetlands that intercept runoff, and time fertilizer. So plants, not waterways, get the feast. Some elements do not stay politely diluted, they climb the food chain. Heavy metals such as mercury, cadmium and lead can bioaccumulate in organisms and biomagnify at higher trophic levels, so a top predator can end up with concentrations thousands of times higher than the surrounding water. In medicine, one countermeasure is chelation therapy. Chelators are claw-like molecules, for example, EDTA for lead, dimecaptosuccinic acid for certain arsenic and mercury exposures, that bind metals using multiple donor atoms, wrapping them into water-soluble complexes that the body can excrete. It is a delicate tool. The same ligands can also grab essential ions like zinc 2+, or calcium 2+, so dosing and selection are done with care. When water carries a whiff of solvent or tastes faintly chemical, activated carbon often comes to the rescue. Made by pyrolyzing and activating carbonaceous materials, it has an immense internal surface area, hundreds to over 1,000 square meters per gram, riddled with pores that welcome organic molecules. Through van der Waals forces and, for some pollutants, specific interactions, activated carbon adsorbs taste and odor compounds, pesticides, and many industrial organics. Packed into filter beds or granular cartridges, it polishes drinking water and protects fish and aquaria. In wastewater plants, it captures hard-to-biodegrade micropollutants that slip past biology. Beneath our feet, soils run on redox rules. Where oxygen is plentiful, iron sits mostly as iron 3 in insoluble oxides and hydroxides that lock phosphorus and some trace metals onto particle surfaces. Let the soil become waterlogged and oxygen poor, and microbes turn to alternative electron acceptors, reducing iron 3 to iron 2, which is more soluble. Arsenic, often adsorbed to iron 3 oxides, can be released under these reducing conditions and leach into groundwater. Manganese shows similar mobility swings between manganese 4 and manganese 2. Drain the soil and oxygen returns, iron reoxidizes and metals can reattach. Managing water tables and organic inputs is therefore chemistry by way of hydrology. Control the redox, and you control what moves. Turning seawater into drinking water looks simple until you pay the energy bill. Desalination leans on two main strategies. Distillation boils water, condenses the vapor, and leaves salts behind. Reliable but energy hungry, because you must supply the latent heat of vaporization, though multiple effect and vapor compression designs recycle heat to trim costs. Reverse osmosis uses high pressure to push water through semi-permeable membranes against the natural osmotic flow, rejecting most salts and many contaminants. Energy recovery devices now recapture pressure from the brine stream, making modern reverse osmosis markedly more efficient than early systems. Both approaches demand careful pretreatment to prevent fouling and scaling. Both produce a concentrated brine that must be managed responsibly. The chemistry is clean. The engineering challenge is to do it with minimal energy and minimal environmental footprint. From swapping out hardness ions to halting algal avalanches, from catching metals with molecular claws to polishing water on carbon's vast internal landscapes, from soil redox switches that open and close elemental traffic to the energy calculus of turning oceans into taps. Environmental chemistry is a toolkit for keeping water and soil healthy, clear and alive. Shine ultraviolet or visible light through a solution, and some wavelengths will be gulped down by electrons leaping to higher energy states. That is UV-visible spectroscopy in a sentence. It measures electronic transitions, and the darker the gulp, the more of the absorbing species you have. The Beer-Lambert law makes this quantitative. Absorbance equals molar absorptivity multiplied by path length multiplied by concentration. In words, A equals epsilon times L times C. Epsilon is the dye's or molecule's inherent ability to absorb at that wavelength. L is how far the light travels through the sample, often 1 centimetre, and C is the concentration. Plot absorbance versus concentration for a standard series, and you can read unknown concentrations straight off the line like a ruler made of light. If UV-Vis tells you how much, infrared spectroscopy whispers what kind. Molecules vibrate, bonds stretch, bend, twist, and each functional group has preferred frequencies, like instruments in an orchestra. An OH stretch near 3,400 wave numbers announces an alcohol. A sharp carbonyl peak near 1,700 wave numbers signals an aldehyde or ketone. The fingerprint region below 1,500 wave numbers is a dense thicket of unique patterns. Record which IR wavelengths are absorbed, and you build a map of functional groups without ever opening the molecule. Nuclear magnetic resonance, NMR, lets you eavesdrop on atoms by listening to their spins in a magnetic field. Hydrogen and carbon nuclei behave like tiny bar magnets. In a strong field, they align and precess at frequencies exquisitely sensitive to their electronic neighbourhoods. Shielding by electrons shifts signals upfield or downfield, so chemical shift reveals what is nearby: an electronegative atom, a pi system, an alkyl chain. Splitting patterns, doublets, triplets, quartets, arise when neighbouring spins couple, counting the number of adjacent hydrogens like notches on a doorframe. Integration tells how many hydrogens contribute to a signal. Put these clues together and NMR writes out the molecule's connectivity in a language of peaks and spacings. Mass spectrometry weighs charged fragments with breathtaking precision. You ionize molecules by electron impact, electrospray, or another method, and accelerate the resulting ions through electrical magnetic fields. Because the path an ion takes depends on its mass-to-charge ratio, m/z, the detector records a spectrum of peaks whose positions and heights reveal both the molecular mass and characteristic fragments. A molecular ion peak hints at the intact mass. A pattern of losses, 18 mass units for water, 15 for a methyl, sketches the functional groups. High-resolution instruments can even distinguish between formulas that differ by a fraction of a Dalton, turning the spectrum into a chemical fingerprint. When you have a crystal, X-ray diffraction is the gold standard for seeing atoms where they live. X-rays reflect and interfere from the periodic planes in a crystal lattice, producing a pattern of spots whose positions and intensities encode the three-dimensional arrangement of atoms. By solving the diffraction pattern, you recover electron density maps and place atoms with angstrom-level accuracy. Bond lengths, bond angles, hydrogen bonds, metal coordination, all revealed. This is how we know the shapes of complex minerals, pharmaceuticals, metal organic frameworks, and even protein structures when they can be coaxed to crystallize. Some molecules do more than absorb light, they glow. In fluorescence, a molecule absorbs a photon and jumps to an excited electronic state, then relaxes a little, losing some energy as heat, before emitting a new photon as it falls back down. Because of that relaxation, the emitted light has a longer wavelength, lower energy, than the absorbed light, a Stokes shift that makes fluorescence easy to spot with filters. Sensitive detectors can see even faint glows. So fluorescence underpins everything from DNA dyes in gels to fluorescent proteins in cells, from environmental sensors that blink when they bind a pollutant to barcodes read by scanners. Light in, a softer light out, and a wealth of information in the colour and brightness of the glow. Chromatography is like sending a crowd through a maze where different people are distracted by different sights along the way. A mixture is carried by a mobile phase past a stationary phase, and each component interacts a little differently with what it passes. Some linger, some dash ahead, and the separation emerges as bands or peaks at different times. Whether the stationary phase is a solid surface or a liquid coated on a solid, and whether the mobile phase is a gas or a liquid, the principle is the same. Different affinities make different speeds, and different speeds make clean separations. When your analytes are small and eager to evaporate, gas chromatography is the nimble sprinter. A tiny injected puff vaporizes and rides a carrier gas through a long, temperature-controlled capillary, coated inside with a stationary phase. Volatile components zip at different rates depending on how strongly they stick to the coating and their boiling points. For larger, less volatile, or thermally delicate molecules, liquid chromatography takes the baton. Here, a liquid mobile phase pushes the sample through a packed column. Gradients of solvent strength, different stationary chemistries, and finely tuned flow rates coax proteins, pharmaceuticals, and polymers to part ways without singeing them. Capillary electrophoresis trades solvents for electricity. Fill a slender capillary with a conductive buffer, apply a high voltage, and ions race toward the electrode of opposite charge. Smaller, more highly charged ions feel a stronger pull and slide more easily through the solution, so they arrive sooner. Bulkier or less charged species lag behind. Because the separation depends on charge to size ratio, you can resolve closely related ions with exquisite efficiency using only microliters of sample and minutes of time, a powerful way to sort amino acids, peptides, and DNA fragments. Sometimes the best sensor is a miniature specialist. Ion-selective electrodes measure the activity of specific ions using membranes that let mostly one ion pass or interact. A glass membrane rich in certain sites makes a pH electrode favor hydronium. Polymer membranes doped with ion exchangers can target nitrate, calcium, or potassium. The potential across the membrane tracks the ion's activity in the sample through a Nernst-like relationship, turning a subtle electrochemical preference into a stable, easy-to-read number, ideal for fieldwork and routine monitoring. Real samples have personalities, pigments, salts, and countless extras that can skew signals. Standard addition corrects for these matrix effects by spiking the actual sample with known increments of the analyte and measuring the response each time. Plotting signal versus the added concentration and extrapolating back to where the line would hit zero reveals the analyte's original level in the unspiked sample. Because the matrix is identical in every aliquot, its mischief is constant and cancels out in the math. It is calibration that speaks the sample's dialect. Internal standards are the analyst's steady hand. Before processing, you add a known amount of a compound that behaves like your analyte, but is distinguishable. A deuterated version in mass spectrometry, a closely related analogue in chromatography. Any variability in injection volume, extraction efficiency, or instrument drift affects the analyte and the internal standard together. By taking the ratio of their signals, You divide out much of the noise, improving precision and accuracy. It is the laboratory equivalent of measuring with a ruler that flexes exactly as much as your sample, so the true length stays true. Lab gear is not a fashion statement, it is a force field. Safety goggles shield your eyes from splashes and flying shards. A lab coat keeps spills off your skin and street clothes. Gloves form a barrier between your hands and whatever you are handling. Tie back long hair, skip loose sleeves, and wear closed-toe shoes. Think of it as dressing for the weather. In this climate, the forecast calls for occasional acid rain and the chance of solvent showers, so bring your own protection. Before you uncap a bottle, read its story. Safety data sheets are the field guides for chemicals, summarizing hazards, safe handling, storage, spill response, and first aid. Flammable, corrosive, toxic by inhalation. The safety data sheet lays it out, along with what kind of gloves actually resist that solvent and what extinguishers to use if it lights up. When something goes sideways, the fastest way to do the right thing is to have already read the page that tells you what right looks like. Waste containers are not suggestion boxes, they're carefully curated destinations. Proper waste segregation keeps incompatible chemicals from meeting again in the dark. Acids and bases go to different drums. Halogenated solvents keep their distance from non-halogenated ones. Heavy metal solutions get their own labelled homes. Mix the wrong things and you can generate heat, pressure, toxic gases, or a mess that cost far more to dispose of safely. Label everything clearly, keep caps closed, and when in doubt, ask before you pour. When you need mass to the milligram or better, treat the analytical balance like a picky musician's instrument. Level it so gravity pulls straight down. Close the draft shields to block air currents that make readings jitter. Let samples and containers come to room temperature so convection does not nudge the pan. Use clean, dry, tared containers. Never weigh chemicals directly on the pan, and handle them with forceps or gloves to avoid fingerprints adding a mystery microgram. Press tar, wait for stability, add carefully and let the numbers settle. Good balance etiquette turns about into exact. Volume too has its specialists. Volumetric pipettes deliver single, precise volumes. Burettes let you dispense titrant drop by drop. Volumetric flasks make solutions to align with exquisite accuracy. Rinse glassware with the solution it will hold, not just water. Read the meniscus at eye level, and remember that to deliver and to contain markings mean different things. Calibrated glassware is the difference between a crispy titration endpoint and a vague somewhere around here, between a standard solution and a strong hunch. And when acids enter the chat, there is one rule you should hear in your sleep. Always add acid to water, never water to acid, to dissipate heat safely. Pouring water onto concentrated acid can flash boil the first drops and blast the mixture out of the container. Adding acid slowly to a larger volume of water lets the heat spread and the solution cool as you go. Stir gently, use a heat-resistant container, and take your time. The rhyme exists for a reason. Do as you oughter, add acid to water. When a titration needs to be right the first time, you start by training your titrant with a primary standard. A primary standard is a compound so pure, stable, and well-behaved that you can weigh it directly, dissolve it, and know its concentration to the last significant figure. Think sodium carbonate for acids, or potassium hydrogen phthalate for bases. Once you've standardized your titrant against that gold standard solution, every volume from the burette translates cleanly into moles, and every calculation stands on solid ground. As the titrant drips in, you watch for the endpoint, the experimental signal that you've reached the neighborhood of stoichiometric equivalence. The equivalence point itself is where the moles of titrant match the moles required by the balanced equation. but we detect the nearby endpoint with indicators or instruments. Phenolphthalein fades from colourless to pink as pH passes through its transition range. Methyl orange turns from red to yellow in the acidic region. Potentiometric titrations track the jump in electrode potential. Conductometric titrations follow a kink in conductivity. Spectrophotometric methods see the absorbance change. The closer your endpoint tracks the true equivalence, the cleaner your numbers will be. Sometimes a reaction is shy or slow and you cannot titrate it directly. Enter the back titration. You add an accurately known excess of a reagent that reacts completely with your analyte, then titrate the leftover excess with a second standard solution. By difference, you learn how much reagent your analyte consumed, and thus how much analyte was present. It is a clever two-step dance. Give too much on purpose, then measure how much is left and subtract to find the amount that actually mattered. Calorimetry turns temperature into a truth serum for energy changes. In bomb calorimetry, you measure the heat of combustion at constant volume. A tiny, precisely weighed sample burns in an oxygen-charged steel bomb immersed in a known mass of water. Because the volume is fixed, no pressure-volume work is done. The observed temperature rise maps to a change in internal energy for the system. First, you calibrate the calorimeter's heat capacity with a standard like benzoic acid. Then you run your unknown and compute the energy released per gram or per mole. It is as close as chemistry gets to a campfire with a spreadsheet. For subtler thermal events, melting points, crystallizations, glass transitions, curing reactions, differential scanning calorimetry takes the stage. The instrument heats your sample, and a reference side by side and records the difference in heat flow as temperature ramps. Endothermic dips mark melting or evaporation. Exothermic peaks flag crystallization or cross-linking. A baseline step reveals the glass transition, where a polymer shifts from brittle to rubbery. Because DSC reports heat flow directly, you can quantify enthalpies of transitions and map how additives, molecular weight, or processing change a material's thermal fingerprint. Whenever mass is your yardstick, drying to constant mass is the mantra that saves the day. Many solids cling to moisture or solvents that masquerade as extra analyte on the balance. By heating or vacuum drying a sample, cooling it in a desiccator, weighing and repeating the cycle until consecutive masses agree within a tight tolerance, you strip away those stowaways. Only then do you trust the number. In gravimetric analysis, this is the difference between a tidy stoichiometric precipitate and a value inflated by a film of humidity. Constant mass means the mass is the chemistry, nothing more, nothing less. When a steak sears or bread crust bronzes, the kitchen becomes a chemistry lab. Maillard reactions, a cascade between amino acids and reducing sugars, kick off around moderate to high heat, rearranging atoms into hundreds of new flavour molecules and brown pigments called melanoidins. The sizzling aroma of toasted nuts, the deep savour of roasted coffee, the complex crust on a loaf, all stem from this controlled browning. Too cool and you get pale and bland, too hot and you drift toward carbonization and bitterness. Dry the surface, manage the heat, and you unlock the sweet savoury fireworks that make cooked food irresistible. Oil and water do not like each other, but they will cooperate when a mediator steps in. Emulsions like mayonnaise suspend tiny droplets of oil throughout water, or vice versa, by using emulsifiers that wear two faces at once. Lecithin in egg yolk has a hydrophilic head that loves water and a hydrophobic tail that loves oil. Whisking tears oil into microscopic droplets. Lecithin lines each droplet, tails in the oil, heads in the water, preventing droplets from coalescing. The result is glossy, thick and stable, and the same trick tames salad dressings, ice creams and creamy sauces. Add the oil slowly, keep whisking, and chemistry rewards you with silk. Fluffy cakes and tender pancakes owe their lift to a quiet gas factory. Baking powder blends a base, usually sodium bicarbonate, with one or more food acids. When moistened and warmed, they react to release bubbles of carbon dioxide that puff the batter. In words, sodium bicarbonate plus acid yields carbon dioxide gas plus water plus a salt. Double-acting baking powders add a heat-triggered acid so you get a first fizz in the bowl and a second in the oven. Too little gas and your bake is dense, too much and the structure sets late and collapses. Measure carefully and mix promptly so those bubbles rise where you want them. In the oven, not in the mixing bowl. The scaffold that traps those bubbles in bread is gluten, a protein network formed when wheat flour meets water and motion. Two families, glutenins and gliadins, bond and entangle into an elastic web that stretches to hold carbon dioxide from yeast or baking powder, then sets during baking to give crumb and chew. Kneading aligns and strengthens this network. Resting lets it relax and redistribute water. Salt tightens it, improving elasticity and flavour. Switch to low gluten flours and you get tender cookies. Push high hydration and strong gluten, and you can coax open, artisanal holes into a loaf. Humble table salt is both flavour amplifier and guardian. A pinch highlights sweetness, rounds bitterness, and wakes up aroma molecules by nudging salivary chemistry and receptor response. In preservation, salt lowers water activity, the amount of free water that microbes need to grow, and draws moisture out of cells by osmosis. From pickles to gravlax, salted cheeses to cured hams, the principle is the same: less available water, slower spoilage. In baking, salt also helps strengthen gluten and moderates yeast activity, guiding fermentation so dough rises with poise rather than racing ahead. Fermentation is the original slow-cooking recruit microbes, and they do the chemistry while you wait. Yeasts convert sugars to carbon dioxide and ethanol, lifting bread and brewing beer and wine. Lactic acid bacteria turn milk into yogurt and cheese, cabbage into sauerkraut and kimchi, and dough into tangy sourdough by producing lactic acid that lowers pH, firms textures, and guards against spoilage. In words for yeast's magic, glucose yields ethanol plus carbon dioxide gas. With the right temperatures, time, and salt levels, fermentation builds complex flavors, gentles textures, and adds a probiotic flourish. Proof that, given sugar and patience, microbes are master chefs in miniature. Grease and grime are stubborn because oil and water avoid each other. Soaps and detergents broker peace by forming micelles, tiny spheres where hydrophobic tails huddle around the oil in the centre, while hydrophilic heads face the water. Agitation breaks the oil into droplets. Surfactant molecules wrap each droplet, and suddenly the mess is compatible with water and can be rinsed away. Hard water can interfere by binding soap into scum, which is why modern detergents include builders and chelators that tie up calcium 2+ and magnesium 2+, so the micelles can get on with the cleaning. Bleach is a controlled blast of oxidation. Household bleach solutions, usually sodium hypochlorite, attack the double bonds and chromophores in stains, snipping them apart so they no longer absorb visible light. The stain quite literally loses its colour. The same oxidative punch disrupts proteins and membranes in microbes, providing rapid disinfection when used correctly. Because hypochlorite is reactive, it should never be mixed with ammonia or acids. Those combinations can release toxic gases. Used on the right surfaces at the right dilutions, bleach turns tough stains and lurking germs into yesterday's problem. Heartburn is an acid-based story with a happy ending. Antacids neutralize excess stomach acid, raising pH toward comfort. Calcium carbonate is a classic. Calcium carbonate plus 2 hydronium ions yields calcium 2 plus carbon dioxide gas plus 3 water. In plain words, calcium carbonate reacts with acid to make dissolved calcium, bubbles of carbon dioxide and water. Different antacid formulas pair the neutralizing reaction with ingredients that reduce gas, coat the esophagus, or act more slowly for longer relief. But the core chemistry is the same. Take the sting out of excess acid by giving it a gentle base to chew on. Sunlight is lovely, but its ultraviolet component can scramble DNA. Sunscreens step in with 2 families of shields. Organic, sometimes called chemical, filters absorb ultraviolet photons and safely release that energy as tiny amounts of heat, protecting skin in the process. Inorganic, often called mineral, filters like zinc oxide and titanium dioxide scatter and reflect, and, when formulated as modern micronized coated particles, can also absorb parts of the ultraviolet spectrum. Broad spectrum protection means covering both UVA and UVB, reapplying keeps the film intact, and using enough product ensures the labeled protection actually happens. It is wearable photochemistry that keeps your skin's molecules in the shapes they were meant to be. Every portable gadget you recharge is a tiny redox factory. In a battery, one electrode gives up electrons, oxidation, and the other accepts them, reduction. Electrons travel through your device doing work. Ions migrate through the electrolyte to keep charge balanced. In a lithium-ion cell during discharge, lithium atoms at the anode become lithium ions plus electrons. The ions slip through the electrolyte to the cathode and tuck into its layered structure while the electrons arrive via the circuit. Charge the battery and the process reverses. Voltage is the push that comes from the difference in chemical potential between the 2 electrode reactions. Capacity is how many moles of those redox moves the materials can perform. Tap water's journey from river to glass is a relay of clarifying steps. Coagulation comes first. A coagulant such as aluminum sulfate is added, neutralizing the charges on tiny suspended particles. Those particles stick together in flocculation, forming larger clumps that settle out or are removed by sedimentation. Filtration catches what remains as water passes through layers of sand, gravel, or membranes. Disinfection finishes the job. Chlorine, chloramines, ozone, or ultraviolet light inactivate microbes so water stays safe as it travels through pipes. Along the way, operators adjust pH, manage hardness, and monitor for trace contaminants. The result is clear, palatable water whose safety rests on well-understood chemistry, carried out on a civic scale. Antoine Lavoisier helped chemistry grow up. In an era when substances seem to vanish in flames and fumes, he proved that matter is conserved. If a metal lost weight while calcining in an open vessel, it was because a gas from the air had joined it. If a candle burned away, its carbon and hydrogen had become carbon dioxide and water. Sealed balances told the tale. Total mass before equals total mass after, once gases are counted. He also swept away phlogiston, introduced careful nomenclature, and named 2 elemental celebrities: oxygen, the acid former in the language of his day, and hydrogen, the water former. With a balance and new names, he gave the field a clear grammar and a law that still anchors every equation we write. Dmitri Mendeleev brought order to a growing zoo of elements by arranging them in a table that made their repeating behaviours visible. And then he did something bolder. Where the pattern demanded a spot but no element was known, he left a gap and predicted the missing element's properties, density, oxide formulas, even how it would react. When gallium, scandium and germanium were later discovered with properties matching his Eka predictions uncannily well, the periodic table graduated from a clever chart to a theory-bearing map. Mendeleev's genius was not just in sorting what existed, but in confidently sketching the coastline of what had not yet been found. Marie Curie opened a new window on the atom by isolating and naming radioactivity as a phenomenon, and by discovering polonium and radium. Working in Spartan conditions, she and Pierre Curie processed mountains of pitchblende to tease out specks of new elements that glowed with an eerie blue light, energy drawn from spontaneous nuclear transformations, not from any chemical reaction. Her meticulous measurements and new methods earned 2 Nobel Prizes, the first shared in physics for revealing radioactivity, the second in chemistry for isolating new radioactive elements. In a field crowded with hazards and skepticism, she defined a discipline and showed that the atom held far deeper secrets than anyone had imagined. The Haber-Bosch process took nitrogen from the sky and put it into the soil. Chemists and engineers learned to drive the stubborn reaction of nitrogen gas plus 3 hydrogen gas yields 2 ammonia by using an iron-based catalyst under high temperatures and high pressures. That clear sentence, nitrogen plus hydrogen makes ammonia, masks a revolution. Fixed nitrogen for fertilizers on a massive scale, breaking centuries of dependence on guano, manure, and crop rotations alone. The same chemistry that feeds billions also taught industry how to tame equilibrium and kinetics with catalysts, pressure, and clever reactor design. A lesson still echoed in plants that make fuels, plastics, and medicines. Auguste Kekulé gave benzene its ring, and with it a rational way to explain its quirks. He proposed that 6 carbons formed a hexagon with alternating single and double bonds, a structure that accounted for benzene's symmetry and its preference for substitution over addition. The later concept of resonance refined the picture, showing that the pi electrons are delocalized around the ring, but Kekulé's insight provided the first satisfying scaffold. With a hexagon in mind, chemists could finally catalogue aromatic compounds sensibly and predict how they would behave, from dyes and explosives to the scents and flavours tucked into spices and flowers. Linus Pauling connected the atom's quantum interior to the shapes and strengths of real bonds, giving chemists a toolkit that still sits on every mental bench. He quantified electronegativity to explain why some bonds are more polar than others. He introduced hybridization, sp, sp2, sp3, to account for the equivalent bonds in molecules like methane and ethene, and he showed how resonance stabilizes structures from benzene to peptide bonds. Pauling's gift was to translate wave mechanics into rules and numbers that could be used at the lab bench, letting chemists draw lines and wedges on paper and know they captured something profoundly real about how atoms share electrons. Some acids are so ferocious that even sulfuric acid seems polite by comparison. These are superacids, mixtures like fluoroantimonic acid, whose effective acidity can protonate extremely weak bases, and, under carefully engineered conditions, even coax a proton onto hydrocarbons. In practice, that means they can generate carbocations that ordinary acids cannot, opening doors to unusual rearrangements and cracking stubborn molecules open for study. They do not just burn, they bend the usual rules of who gets protonated, and they must be handled with elaborate protection and non-reactive containers because almost everything looks like a snack to them. Deep inside gas giants, pressures climb to mind-bending levels, and hydrogen, the simplest element, may take on an exotic role. Squeezed so tightly that electrons roam freely, hydrogen is hypothesized to become metallic, conducting electricity like a wire. If present, this metallic hydrogen layer could help drive the immense magnetic fields of planets like Jupiter and Saturn. On Earth, reproducing those conditions requires diamond anvil cells and shock compression. The research pushes the limits of high-pressure physics and keeps the periodic table feeling alive and a little mysterious. Imagine a solid that is mostly empty space, a ghostly scaffold that stops a flame but barely tips a scale. That is an aerogel, an ultralight high-porosity material formed by replacing the liquid in a gel with gas without collapsing the structure. Silica aerogels can have internal surface areas larger than a football field per gram, making them superb thermal insulators and capable sorbents. They feel like frozen smoke, look like blue-tinted haze, and serve in applications ranging from space dust collectors to lightweight windows and cryogenic blankets. Some fluids refuse to behave. Non-Newtonian liquids change their viscosity when stressed. A pool of cornstarch in water will flow like cream if you dip a finger slowly, but punch it and it turns rigid under your fist. The trick is that particles in the slurry jam together when sheared quickly, shear thickening, forming a temporary solid network that collapses when the stress relaxes. Other formulations do the opposite, thinning under shear, which is why ketchup flows more easily after a few determined shakes. Viscosity, it turns out, can be a mood. Light without heat feels like a magic trick until you meet chemiluminescence. In these reactions, the energy released creates an excited electronic state in a product. When that state relaxes, a photon is emitted. Crack a glow stick and the mixing of reagents starts a cascade that ends with a dye lighting up. Steady, cool radiance follows without a hot filament or flame. Chemists harness this for sensitive assays. One molecule triggers a glow you can measure, and artists use it for the quiet drama of night runs and concert waves. And when you narrate chemistry, clarity beats speed. Balance equations and say them like a recipe so the ear can follow. 2 hydrogen gas plus 1 oxygen gas yields 2 liquid water. Give coefficients, name phases when they matter, and keep the verbs simple. Yields, forms, produces. The goal is a picture the listener can hold in their head, with every atom accounted for and every step easy on a sleepy mind. If you've drifted this far with me, you've travelled from the heart of the atom to the rise of a loaf of bread, from the glow of a diode to the quiet work of enzymes, all by following the same simple thread. Tiny particles sharing energy and arranging themselves into patterns that make our world feel familiar, delicious, colourful, and alive. Chemistry isn't just lab coats and glassware. It's the steam curling from your tea, the silvering of the evening sky, the scent of rain on warm pavement, and the way a favourite sweater feels just right on a cool night. It's the language matter speaks when it tells its best stories. As you settle in, let your mind replay a few gentle scenes, electrons finding their favourite seats, molecules holding hands, crystals growing one patient layer at a time, oceans breathing in and out through carbon and light. Every reaction has a reason, every structure a purpose, and the same rules that guide a star's furnace also guide the rise of a cake and the sparkle of clean glass. That's the quiet miracle of it all. One set of principles, countless cosy outcomes. Thank you for spending your evening with me here on The Sleepy Scientist. If a thought or a question is lingering at the edge of your pillow, tuck it away for the comments. I love hearing what sparked your curiosity. And when you wake, the wonders will be right where you left them. In the kitchen, in the garden, in the sky, and in the little beaker of your morning coffee. For now, though, let the molecules keep working while you don't. Breathe in, breathe out, and imagine the soft, steady hum of atoms doing what they do best, arranging, balancing, and quietly keeping the universe together. Good night, sleep well, and may your dreams be delightfully elemental.